Uh, s- Hi everyone, welcome to the third day of HotNets. We now have this exciting session on programmable networks. I'm Radhika Mittal. I'm an assistant professor at UIUC, and I'll be chairing the session along with Aditi. Aditi, can you please briefly introduce yourself as well?
Sure. Hi, everyone. I'm Aditi. I'm a graduate student at UIUC, and I'm advised by Professor Radhika and Professor Brighton here.
Okay, so I think without further ado, we can get started with our first talk. But before that, just a quick reminder on how to ask questions. So we encourage questions at the end of the talk. If you are signed into the Zoom session, you can raise your virtual hand and then we can unmute you and you can ask your questions. And if you are watching the YouTube stream, you could post your questions on Slack. So we have per channel Slack channels where you can post your questions. You can browse the channels and find the paper and post your questions there. So yeah, please do ask questions. And yeah, so let's get started with our first speaker. So our first speaker is Maria Apostolaki. She's a final year PhD student at ETH Zurich, where she's advised by Professor Laurent Van Beaver. Her research focuses on internet routing and its implication on security and performance. And Maria is on the academic job market this year. Good luck, Maria. And she'll tell us about profile-guided optimizations for P4. So, Maria, maybe you can turn on your video and share your screen.
Do you see it now?
Yes, we do.
And you can hear me as well, right?
Yes.
All right, great. So thanks a lot, Radhika, for the introduction. So as we know, programmable data planes enable a programmer to define the forwarding behavior of a network switch using a high-level language such as P4. In practice, though, such a program often fails to compile. This happens because the programmer needs to map an often ambitious high-level P4 program to the particularly tight resource budget of a typical switch, begging the obvious question: who should fix this, the programmer or the compiler? On one hand, the programmer knows the intended functionality, but he ignores the hardware specifics. As a result, the programmer tries to make the program compile by blindly rewriting semantically equivalent programs and resubmitting them to the compiler. On the other hand, the compiler knows all hardware constraints, but it ignores the context. As a result, the compiler tries to make the program compile by trying out different allocations while conservatively accounting for all possible inputs, including unrealistic or infrequent ones. In essence, there is a gap between what the programmer intended to achieve with the program and what the compiler considers when compiling it. With this in mind, we built P2Go, a system that bridges this gap by generating programs whose compilation is easier to achieve because their scope is limited to the expected case. Instead of putting the burden on the programmer, P2Go generates such programs automatically, guided by the program's profile. The program's profile describes the program's functionality in practice and can be obtained by observing the behavior of the initial program when presented with realistic traffic. Once P2Go generates a new program, say P4 prime, it probes the compiler to verify that it uses less resources, thus the modification made in the initial program are useful. Once the gain is guaranteed, P2Go asks the programmer to verify that P4 prime also satisfies the initial functionality of the initial program. P2Go is a system for P4 profile-guided optimizations, which we designed and built together with Patrick, Alex, and Laurent at ETH Zurich. This is the outline of my talk. I'll first explain what profiling is and how we can profile a program. Then I will talk about the optimizations that P2Go applies to programs and describe our initial results. Finally, I will discuss future directions. So, what is the program's profile? A program's profile is a description of the program's behavior during runtime. In the context of P4, the program's profile contains the control paths that packets of a realistic traffic trace take in the program's control logic. By realistic, I mean that the traffic trace resembles the traffic that the program is expected to run on. For example, the profile of a given program might contain information such as that a certain set of actions are mutually exclusive, that is, that they're never executed by the same packet, or that another segment is very frequently used. P2Go obtains the profile offline. To do so, P2Go first instruments the P4 program. The instrumented program appends the path of its packet through the control logic as a header after its initial header. Next, P2Go runs the instrumented program on the traffic trace that the programmer has provided and collects the output to construct the profile. Once the profiling is done, its insights can guide a broader spectrum of optimizations for compiling the program. P2Go uses 3 profile-guided optimizations in order to reduce the number of pipeline stages the program uses. Indeed, the number of pipeline stages is one of the most scarce resources that often prevents programs from compiling. Concretely, P2Go optimizations aim at increasing the pipeline concurrency, reducing resource waste, and improving the hardware-software split. I'll now walk you through each optimization using a motivating example. Consider the P4 program shown in the slide with 4 tables, namely SYN forward and magic tables 1 to 3. The former is only applied on SYN packets, while the latter 3 on packets whose payload is above 10 bytes. The program needs 5 stages to run in hardware. If you're wondering why 4 tables need 5 stages, then consider 2 things. First, there is a dependency between the SYN forward and the magic tables, meaning that the magic tables use results that could have been changed by the SYN forwarding. So the execution of the SYN forward table needs to precede the execution of the magic table in the pipeline. Second, Magic 2 uses more memory than what is available in single stage. Again, the 2 factors leads the compiler to map the P4 program to 5 stages. Now, I will explain how P2Go leverages the profile of the example program to reduce the number of pipeline stages it uses by applying 3 optimizations. In the first one, P2Go aims at increasing the pipeline concurrency by removing potentially fake dependencies. To do so, P2Go first extracts the program dependencies from the compiler. Obviously, these dependencies are found by static analysis on the program. Next, P2Go compares these dependencies with the execution paths taken by packets during profiling. Observe that the dependency between the SYN forward and the magic table one does not manifest during profiling, as no single packet ever matched both. In fact, the compiler does not need to keep them in 2 separate physical stages. Leveraging this, P2Go automatically generates a new program with a dependency resolved, meaning that there is now a clear indication that the 2 tables are mutually exclusive. In fact, the compiler is now allowed to move the magic table in the same states as the SYN forwarding table. By probing the compiler, P2Go verifies that the modification in the program results in a reduction of the required physical stages. Once the gain is guaranteed, P2Go asks the programmer whether the profile-based observation that guided the generation of the new program is general and can be leveraged by to decrease the number of pipeline stages used. The programmer considers the observation and realizes that it is general. Observe that there is no SYN packet with payload, so P2Go's change in the P4 code does not modify the program semantics in practice. After removing the potentially fake dependencies, P2Go searches for opportunities to sort out the pipeline length by slightly reducing the memory of any table. This opportunity might arise in practice due to the lack of knowledge of the underlying architecture. For example, the programmer might ignore the amount of available memory per stage. To do so, P2Go first finds the tables that were least used by packets during profiling. Then, P2Go generates code with reduced memory on those tables and probes the compiler to see if the reduction has a collateral effect on the number of stages used. If there is such an opportunity, P2Go searches for the minimum memory reduction that could shorten the pipeline. In our case, P2Go finds that it can save a stage by reducing the memory allocation by magic 2 only by 2%. P2Go communicates this optimization opportunity to the programmer, who happily accepts it, as his initial choice of memory allocation was only a rough estimate. The last optimization that P2Go applies is migrating code to software. To do so, P2Go first finds the least used tables in the profile and verifies that they're self-contained. That is, no other table depends on their computation and vice versa. In this case, the magic table 3 is a suitable candidate. Next, P2Go generates a program without the magic table that instructs the corresponding packets to be forwarded to the controller. P2Go suggests the edit to the programmer with the profile-based observation that guided it, meaning the fact that magic 3 table was very seldom used and also self-contained. In this case, the programmer refuses and insists that the table magic 3 should stay in the data plane. The profile-guided optimization in this case was not helpful, But let me explain why this can happen and why this is still okay. The traffic trace used during profiling might happen to not contain traffic on which the table is applied. In our example, that was Magic 3. In other words, the trace might not be representative with respect to the observation. Yet, the programmer can easily spot this mismatch when he reviews the observation that guided the optimization that P2Go used, and then reject the suggested optimization like he did in our example. While intuitive, these observations are enough for P2Go to reduce the resources used by realistic programs, as we see in our preliminary evaluation. In particular, we ran our P2Go prototype along the Tofino compiler on 3 realistic examples written in Tofino P414. We generated the traffic on our own and allowed P2Go to use one optimization in each example. As we see in the last 2 columns, P2Go manages to decrease the number of stages that the programs used. We believe that P2Go is the first step towards a new direction for compiling P4 programs. P2Go also raises many interesting questions. First, how practical is it to get a representative traffic trace for profiling? The leverage of P2Go is that the trace needs to be representative only with respect to the observation used to optimize the program. An alternative approach would be to do online profiling and dynamic compilation. The question that remains, though, is, does online profiling worth the cost of monitoring, recompiling, and loading new programs dynamically? And if we cannot have a representative traffic trace, then the generated programs will not always be semantically equivalent in practice. P2Go avoids such negative effects by asking the programmer to approve the change. Obviously, this is an improvement, as a programmer does not need to consider...
2 minutes left.
The programmer doesn't need to consider all possible changes in advance, manually change the program, and manually check again whether those would reduce the compiler's location. But the obvious question is, could we optimize P4 programs without the human in the loop? If we do not want the programmer in the loop, and we also cannot have a perfect traffic trace, then the behavior of our optimized program might diverge from the original under unusual traffic or even adversarial traffic. So the obvious question is, could we detect that there was such a divergence? And if so, could we even provide a fallback? Actually, Nokia's talk from yesterday that she talked about online safety assurance nicely correlates here. Finally, P2Go only targets stages. While this is a good first step, we need to think how to go around other resources such as memory, PHVs, and so on. Optimizing across multiple dimensions increases the optimization space. So how can we best navigate this space? And with this, I concluded my talk about P2Go, a system that bridges the gap between the programmer and the compiler. To do so, P2Go leverages the program's profile to optimize it while not breaking the program semantics under the expected case. P2Go only requires the programmer to approve the optimized program given the observation used together with the achieved gain. And finally, I want to mention that I'm in the academic job market, so please reach out if your university is hiring. Thanks a lot.
Thank you, Maria. That was a great talk. So we can start taking questions now. So if you have a question on the Zoom session, please raise your hand. And you can also post your questions for Slack. All right, so I think the talk was extremely clear. Okay, Arijit Panda, we have a question from him. Let me unmute you. Oops. Okay. Okay, yeah, Panda, can you speak up?
Yeah, wait, can you hear me now?
Yeah.
Cool, so that was a great talk. So one issue that often comes up when applying Pogo to traditional things, so like, Windows for a while used to ship with Pogo enabled, and one of the biggest problems became debugging. So in this case, given that the profile drives the optimization, how does this affect debuggability and especially like a resource debugging where you suddenly see that a change in traffic pattern is causing bad performance? How do you expect programs to debug the output of P2Go?
Can you a little bit clarify your question? I'm not sure, like debugging with respect to what? The use of resources? So it might be that the new use of resources is suboptimal with respect to the beginning, or is this what you're aiming at? Can you hear me?
Well, so yeah, sorry, I muted myself and then couldn't unmute myself, so it was not your. So there's two parts to this. So the first is with terms of resources. The second is, you're changing the layout, and in some sense, while your transformations that you're. So in this case, okay, so the set of optimizations you're doing now are just changing resource layouts, which might be suboptimal for a certain workload. As you go into more and more profile-guided optimization, at some point you start doing transformations on the actual semantics of the code. Means you hope to preserve semantics, but you're changing that. And in both cases, suddenly, the problem is that with general optimizations, you have to you try to de-optimize or try to reason about the optimized version. With Pogo, like as it's driven by by profiles, the optimizations are quite unexpected at times. So. Do you think this problem is easier in the P4 context than because Pogo's been around for order 10 or 15 years now in almost every compiler, and we haven't seen a lot of uses for it.
Okay, so I'll first answer with respect to P4, and then we can talk about the use in general. So, and thanks a lot for the question. It's now I understand it, and I think it's great. So. First, I like to think of P2Go as Grammarly. So Grammarly will not always be right, but sometimes it will be right and it will help you and it will save you time, right? But sometimes it will try to change your semantics of what you're writing. And in this case, you will reject. So the programmer has always the last word of whether he or she wants to actually proceed and do the optimization asked, right? So what we're aiming at with profile-guided optimization in this context is that the programmers should not know everything about the hardware, but they should have somebody telling them what might help their allocation. But of course, it cannot do everything. With respect to whether profile-guided optimizations used, I think they're actually used, and you can find both Facebook and Google have tools like Propeller and Bold that are actually using profile-guided optimizations today. So I don't know. I think I'm excited about this direction.
Can I ask there's actually a question, so I will.
Yeah, so maybe Lloyd can ask a question. Yeah. Okay, thanks for your question, Panda. Okay, Lloyd, I'll ask you to unmute yourself, and you can.
Yeah. Can you hear me?
Yeah.
Great. So thanks for the talk. Really interesting. So it seemed like the first optimization you made that saved you a stage was you leveraging this insight that SYN packets have a small payload, and that seems to be kind of independent from the actual traffic trace. And so you could imagine that if you had some default traces that maybe sent a bunch of SYN packets and some other packets, that you could get these optimizations without having a real traffic pattern. So do you think there's maybe an opportunity to have some default traces that give you some optimizations?
Yes, definitely. In fact, how useful the profile-guided optimization will be depends on the trace, but the trace doesn't have to be perfect. So it will be useful if the trace is representative with respect to the observation that P2Go uses. So in this case, the observation that P2Go uses applies to any possible trace. So yes, totally. And this is the beauty of it, that you don't need a perfect trace to start, right? But the better trace you offer, the more optimizations you can actually achieve with it.
Yeah, thanks. Awesome.
Thanks. So I think we can take one last question. So there's a question on Slack. Aditi, could you please relay that question, and then we can move next.
Sure. So Hardik Soni asked a question. He says, how about punting packets with complex and or rarely seen headers to the controllers? There could be two reasons to do it. One, removing such headers could greatly simplify PHP allocation and will help to fit the program. Two, some headers are part of purely control protocols, therefore with reasonable latency in processing them could be tolerated.
Yeah, that's also a very good point. I totally agree with that. So we are not, of course, when we're moving things to the controller, right, we need to pay the price of actually the extra delay that their processing will cause. And it's true that in P2Go, we only take into consideration the percentage of packets that would actually end up being in the controller. in a future project, we could take more fine-grained information into consideration and then take a more informed decision on what we want to move in the controller. But the thing is more of trying to make the device act a bit like a cache of the instructions, in that you move there whatever is very frequently used or whatever would cause a lot of delay in the actual traffic if it is in the software. So more of trying to rethink how the split should be done rather than making it arbitrary, right? But that was a valid point, yes.
Thank you, Maria. That was a great talk. So with this, we can move over to our next talk. Aditi, would you like to introduce the speaker for the next talk?
Sure. So the second talk that we have in this session is titled Challenging the Stateless Core of Programmable Switches. So this paper will be presented by Nadine Guevara, who is a PhD student at Imperial College London, and he's supervised by Paolo Costa. Her research focuses on hardware architectures, programmable logic, and systems. So with this, I guess Nadine can get started.
Okay. Sorry. Okay. Can you hear me?
Yeah.
Okay, sorry, let me just get rid of this. Okay. Hi, I'm Nadine, and I'm going to be talking with you today about the revolutionary programmable switches. Not only can these switches support line-rate programmable packet protocols, but they further enable the new class of in-network applications. However, these in-network applications are quite different from the packet protocols these switches were originally designed for. And as a result, supporting them can be not only challenging to the programmer, but often constraining. And in that, we see an exciting opportunity moving forward to rethink the current architecture of programmable switches, such that they can also better support the features of network applications.
Nadine, sorry to interrupt, but are you changing slides? We are just seeing the title slide, actually.
No, I'm about to change.
Oh, okay, sorry, yeah.
Actually, yeah, it is frozen. 1 second. Okay, did it change?
Yeah.
Okay. So let's start by looking at the current architecture of programmable switches. So at a high level, a protocol-independent switch pipeline comprises of multiple match action unit stages. And usually a program is written in match action primitives, and then tables in these stages are programmed accordingly. So once a packet arrives, the packet headers are written into a packet header vector. And this packet header vector serves as input to the first match action unit stage. And depending on the configurations in the tables in the stage, certain actions are performed depending on the matches. And these are usually simple operations that are typical of packet protocol programs. And some states, such as counters or statistics, can also be retained in these stages. Then this packet header is fed forward to the next stage. And it's worth noting that these stages are completely independent, and state as well as match table configurations cannot really be accessed from any other stage. And once this repeats across all stages in the pipeline, the headers are recombined with the payload, and then the packet leaves the pipeline. And in order for switches to support higher rate, groups of ports are usually assigned to a certain pipeline. And we have many of these pipelines that operate in parallel. And just like the match action unit stages, these pipelines are similarly completely independent. That is, everything in each pipeline can only be accessed by the packet that's actually moving through that pipeline and not from another pipeline. So in addition to supporting these packet protocols, there has been a new wave of in-network applications that can be implemented on these switches. So what do I mean when I say in-network applications? Traditionally, applications only run on servers on the end host, and switches only handle networking operations and routing. However, with this recent programmability, parts of applications can now be offloaded onto the switches themselves. And this actually proved quite beneficial for many applications. For example, in distributed storage systems, if we cache hotkeys and values in some of these switches, we can reduce the service latency because now the request is serviced immediately in the network as opposed to having to go to where it's urgently stored in a backend server. Other applications like distributed machine learning could observe higher throughput as well as a lower network load by performing aggregation within the network itself. And this vantage point also proves beneficial to distributed system coordination and telemetry because you can actually do things from within the network itself. However, there are two things worth noting. We realize that in network applications, unlike packet protocol programs, are better represented using data structures and data structure operations as opposed to match action rules. And even more, they actually focus mainly on state. So their operations depend on the state and their updates target the state rather than the packet headers themselves, which is also typical of packet protocol programs. And observing this, it's important to pause and reflect whether this impacts how well network applications can be implemented on current architecture. So the main contribution of our work is reflecting on how the properties of the architecture can be limiting potentially to network applications. So in the case of a network application, a packet arrives and the critical factor in it or unit is the state itself. You could extract as well some header fields, but we are going to focus on the state. And the state is then sent to the action unit similar to packet protocol programs. However, since packet protocols usually involve simple operations, these action units can do complex operations that need to access a lot of state, which could be potentially stored in data structure. So if you imagine you have here a large list and you want to find the minimum of one of the items on this list, you can't really do that. And you need to think of that while implementing your code and partition your data structure across all the stages such that you abide to the constraint of the accesses you can do within the stage. And note that by doing that, now the size of the data structure depends on the number of stages you have rather than the total memory you could potentially use on the switch. The next limitation is observed due to the fact that stages can't really access state and other stages. And as a result, if you want to communicate some state, you now need to rely on the packet header vector as the means to propagate state through the pipeline instead of using it to move on packet headers that are operated on. And this creates a dependency between the size of the packet header's metadata field and the state you can propagate. And even more, you notice the state is only fed in the forward direction. So that means assuming you have an update operation that is a result of an operation of this data structure, the only way you can support it is by recirculating this packet header vector back to the beginning of the pipeline. And you need to account for that while programming, as well as you risk the performance of the switch because recirculation can degrade the throughput. And even more, it could violate the correctness of the program itself, since by the time this has arrived here, stage one state might have been modified by another packet. So the fourth limitation that results from the fact that you have this feed-forward state is a limitation in how you program your code. Since you need to keep in mind the fact that variables are mapped to potentially specific stages, and that means if you write your code whereby A is accessed before B, and at some point you decide to change the access order and access B before A, then you might have a compiler error that says your code can't be implemented on the switch. And to make things even more complicated, pipelines don't share any state. So now you have a group of ports and packets could arrive at any port, and then your state is only stored in one of these pipelines. So that means the packet needs to go to this single pipeline, and this pipeline needs to service all the packets of the application, increasing the load on the pipeline. And imagine scenarios where the destination of this packet is not a port attached to this pipeline. Then this packet has to be routed all the way back through the scheduler and then through potentially another port, thereby also increasing the packet's latency. So observing these limitations, we see that we actually have quite an exciting opportunity going forward to rethink this architecture with in-network applications in mind and not just packet protocol programs. And a lot of other works have actually noticed that implementing applications on switches can be quite challenging. So some solutions include making the programming language simpler, and one work actually today is going to address that as well, along the lines of supporting data structures. Other approaches are relaxing some of these limitations, such as supporting more complex operations within a stage or supporting more flexible memory accesses. But they are still restricted to the pipeline, and each one of these results in its own set of trade-offs. And other radical approaches propose adding configurable stages within the pipeline, but this actually makes the pipeline more complex, and it increases the latency for all packets, regardless of whether or not they are using these configurable logic blocks. Instead, we are inspired by the way the PISA pipeline is designed. So if you think about the PISA pipeline, it was designed with packet protocols in mind, and it supports what they need quite well. And we take an orthogonal approach where we complement this pipeline with a stateful pipeline with the basic idea that the heart of this pipeline is data structure instance blocks. And these instance blocks can be optimized specifically to perform the data structure operations that are typical of these stateful and network application. And as well as that, they could potentially support more parallelism, even with shared memory and shared state, because you have a better knowledge of the memory access pattern of data structures, and you could synchronize them accordingly and optimize for them, rather than designing your pipeline to support any potential access pattern and any operation. However, we keep in mind that ultimately this pipeline executes in parallel to the original pipeline. And the PISA pipeline has a slack time or latency, which is the time it takes a header to traverse this pipeline. So provided all the operations that complete in the stateful pipeline match the time of the packet header processing that happen in the PISA pipeline, and we don't really block packets here, potentially by also pipelining or leveraging parallelism, we actually ensure that we do not hinder the original performance of the PISA pipeline. So in conclusion, network applications are quite different from packet protocol programs, and supporting them on PISA has been observed to be challenging. So we see an exciting opportunity for the entire community to consider how we could actually do an even better job to unlock new applications with an architecture that's better designed for them. And we're only at the beginning of our journey here, and there are a lot of open questions which we are excited to tackle. For example, what could potentially be the best way to implement the data structure instance blocks, as well as the platform, which could range from customized FPGA logic blocks to processor logic with memory management unit, the performance cost trade-offs of each one of these approaches. And ultimately, we also want to provide a friendly programming experience. So it's important to look at how we can also do a good job supporting our underlying hardware architecture with the right software tools. Thank you, and I look forward to hearing your questions.
Great talk, Nadine. Thanks a lot. We have a question from Sheer. So Sheer, if you can unmute yourself and ask your question.
Sure. Hi, Nadine. It was a great talk, and I really like this idea, and I think it has a lot of potential. I was wondering how you would ensure that the programs on this additional pipeline would actually run at line rate. Do you have any way to make sure of that?
So the idea is
potentially be.
If we start by prototyping our designs, let's say by implementing them on an FPGA, ultimately your programmable logic blocks are going to be running potentially at a certain clock rate as well. And you'll be running them with a certain bus width that's feeding into this pipeline. And then depending on that, you could start by saying, if we pipeline our design right, then we know that this is the rate of bits per second that would be traversing this data structure by having a pipeline architecture. I think it would be less predictable in cases where you can have unexpected stalls in the pipeline. But the idea is, if such cases occur, you can actually have many pipelines running in parallel and ensure the worst case execution time, potentially including the stalls, does not exceed that. And in terms of the slack duration, then current, let's say, P4 programs, when you compile your code, you have the idea of the latency of your pipeline, and the same thing could be used, basically. Thank you.
Thank you.
Okay. Are there any other questions? Okay, so Theo Gibson, he has a question, but he can't raise his hand. Theo, let me try to look you up and okay. Theo, you should be able to unmute yourself. Yeah.
Hi, that was can you hear me?
Yeah, we can.
That was a great talk. I've been personally, I've struggled with writing stateful applications for these devices. So, why do you think this pipeline, this parallel stateful pipeline, belongs on a switch? Do you think it should be in a separate device just for stateful processing? Why should it coexist with this other pipeline?
So thank you very much. That's an interesting question. So honestly, it doesn't need to exist. It could be a completely separate chip that's co-packaged in the same system. However, the main idea is since the parser already extracts the relevant header fields for the PISA pipeline, and your packets ultimately need to be processed by some packet header processing, as well as other stateful processing. That way you could have the best of both worlds, where these things are running at line rate side by side, and you also have the advantage of doing things in the network. But there is no really strict restriction on the fact that they have to be on the same chip. Does that answer your question?
Theo, you're muted in case you were saying something. All right. I guess we can move on. So I had, there's some questions coming up on Slack. Maybe you can answer them offline on Slack. But I had a quick question. So to me, like one of the main limitations of programmable switches in terms of running in network applications is just the amount of memory that's available. So do you think that like your approach with the new architecture would also allow better utilization of memory, like when it's not split across stages and when you can like maybe use memory?
Very good. I should have pointed that in the presentation. Thanks for asking. So yes, exactly. So the fact that you have this on the side, like there are actually techniques to hide memory access latency. Mm-hmm. And on the current architecture, you can't really have the flexibility of leveraging such techniques. However, by having the separate pipeline, the idea is you can make more useful, more flexible use of the memory and design things such that you could account for that as well. Thank you.
Great, thanks. So I think we're running out of time, but there are more questions on Slack, so please continue the discussion there, and we'll move over to our next talk. So our next talk is on distributed shared state abstraction for programmable switches. The speaker is Lior Zeno. He's a PhD student at Technion, where he's supervised by Mark Silverstein, and his research focuses on programmable networks. Okay, so Lior, you can take it over.
Thank you very much. So I'll present our work on distributed shared state abstractions for programmable switches. And this is a joint work with our great collaborators at MSR, Dan Ports and Jacob Nelson, as well as my advisor, Mark Silverstein. So the enabler for this work is the recent advances in networking hardware that paved the way to highly performant network processors. So these devices essentially break the status quo of programmability equals slow performance by offering the same level of performance as fixed function switches, while also providing data plane programmability at the same cost. And this technology attracted many researchers to demonstrate the performance benefits of in-switch acceleration. And this there are many projects on that, and they range from network functions that are shown in green on these slides, like load balancers, DDoS detectors, and network monitoring applications, all the way to general purpose applications, which are shown in green, such as database accelerators, network sequencers, and key value stores. And one thing to note here is that all these applications are stateful. So basically they utilize P4 stateful objects like registers and counters, which enables the developer to update the state in one packet and then read the state in the next packet, all at line rate speed. And in this work, we're going to focus on network functions. So while previous works have shown the benefits of in-switch acceleration, they all suffer from one primary limitation, which is they all run on a single switch or focus on a single switch design. However, we argue that in order to be practical, network functions must run on multiple switches. So one reason for that is if we deploy a network function on a single switch, it effectively forces all the packets of interest to travel through that single switch, and therefore it severely limits the scaling out. Another reason is that a single switch is only a partial view of the network in networks that support MPTCP or deploy dynamic routing protocols. And finally, in order to provide high availability, we have to deploy network functions on multiple switches. However, the main problem with running a stateful network function on multiple switches is the distributed management of its state. So to better understand this problem, we can take a look at a heavy ethers detection application, which is widely used in DDoS detectors. So this application has to alert whenever a flow exceeds a certain number of sent packets. And in this example, we are interested in flows that sends more than 1K packets in a window. So one way to implement this application on programmable switches is by maintaining a per flow counter. And this counter can be updated directly in the data plane without the mediation of the control plane. And in this particular example, we can see that flow number 2 has exceeded its threshold, therefore an alert is triggered. However, when we are interested or looking at network-wide heavy ethers, it is not enough to monitor locally at each switch. And the reason is that large flows may fall under the radar. And if we lower the threshold at each switch, we're going to get a lot of false positives. So one way to achieve a global view is by adding a centralized controller. And this controller can collect the counter values from the switches, aggregate the values, and then report the heavy ethers. However, there are two main limitations to this approach. The first one is that it doesn't scale because the update rate is limited to the throughput of the controller. But more generally, this solution is ad hoc to this specific problem. Specifically in this case, there is no single point in time where the controller is guaranteed to have the most up-to-date value of the shared state, implying that if we look at other applications that may need the more precise values of this shared state, they won't be able to use the same protocol. So essentially, developers will have to rewrite it from scratch. So what we are looking for is a generic solution that can be reapplied in different setups and while it being efficient. So in this work, we propose to manage the shared state entirely in the data plane. Our primary observation is that distributed shared state management requires a principled approach. So as you know, many replication protocols were already developed and established in the distributed computing literature and applied to standard computing system. So we can reduce our big problem into the following question. How can we intelligently map or efficiently map these protocols into the unique requirements of in-switch programming? So the first step is to analyze the access pattern of popular network functions. So we categorize them in the consistency right frequency domain. And for example, we can think of a load balancer, a stateful load balancer, which aims to uniformly route TCP connections among multiple hosts. Because it is essential for all packets of the same TCP connection to be routed to the same server, the load balancer must maintain a connection to server mapping. And once the mapping is decided, we want all the packets of a certain flow to be routed to the same server, implying that this application requires strong consistency. However, it doesn't frequently update the state because we change it only when new connections are established. On the other end of the spectrum, we can think of a DDoS detector application that is based on an approximate data structure called data sketch. So this application can utilize this data sketch to track the frequencies of the packet IPs. And using that approximation, we can try to analyze if the network is under an attack. So because this application already uses an approximate data structure and relies on approximate results, it can also tolerate weak consistency. So from this graph, we draw two main observations. The first one is that applications that require strong consistency are read intensive. And the second one is that write intensive applications can tolerate weak consistency. We also noted at this point that providing strong consistency semantics for write-intensive applications is an open research question. And if we would be able to do that, we can break the wall of it. So it will enable us. To broaden the scope of this work beyond network functions to general purpose applications. So in SwitchMem, we support 3 types of registers, and each register is optimized for different purposes and is accessed through a different protocol. For example, eventual write optimized registers or EWO registers offer low read and write latencies, but they only provide eventual consistency. While strong read optimized protocols trade write latency for strong consistency semantics. In the next slides, I'm going to explain how EWO registers work, and you can find more details on our read optimized protocols in the paper. So the way to implement these registers is to consider the unique properties of the hardware. We follow 2 design principles in SwitchMem design. The first one is that we don't have a lot of memory in the data plane, implying that we won't be able to buffer packets in the data plane. And the second principle is that communication is cheap, implying that we might be able to utilize more frequent updates between the switches. And we will use these design principles to reason about our design choices in SwitchMem. So let's take another look at the heavy hitter detection application. But now, instead of relying on a central controller, we are going to implement it using EWO registers. So in EWO, reads are always performed locally and writes are applied asynchronously. In addition, counters are sharded. So at each switch, instead of maintaining a single counter per flow, we are going to maintain a vector of counters. And this is basically mapping CRDTs, which are well-known data structures from the distributed computing literature, into the switch environment. So how does it work? When a packet arrives at the switch, it updates its local state and then sends a write request to the other switches. But now the receiving switch must be able to merge updates from other switches with its local state. In general, this is a very complex problem, but in some cases, like we have here, like a counter, we can do it systematically. And the way we do it is by taking the larger value of the received state update and the one that we already have locally. Finally, to read the counter value, the switch has to sum all the elements of the vector. So the most obvious challenge here is that updates may get lost. And the way we tackle this challenge in EWO is by using periodic synchronization. Essentially, every period, each switch is going to broadcast the entire vector to all the other switches. And if we take a look at an extreme case where each switch is going to send 10 megabytes, which is the full memory size, and it's going to do that every 1 millisecond, then the total bandwidth that is going to be consumed by this process is about 1% of the total bandwidth that's available on the switch. And this is an example where we can leverage the strength of the switch. From a more general perspective, though, we envision that switch mem is only the first step towards a broader one big switch abstraction, which aims to enable the automatic transformation of a single switch application to a distributed one.
20 seconds.
To conclude the talk, smart switches need abstractions. In SwitchMem, we propose the principled approach to the distributed shared state management problem. Instead of reinventing the wheel, we map proven and tested replication protocols while highlighting the strength of the switch and avoiding its weaknesses. We believe that providing general abstractions instead of ad hoc application-specific solutions is essential to the adoption of programmable switches in production environments. Thank you, and I'm happy to take your questions.
Thank you for the talk, Leo. It was very interesting. So if you have questions, you can raise your hand. Okay, so Meena. Meena, you should be unmuted now and ask your question.
Hi, this was a very interesting talk. Thank you. I was just wondering, do you have like a separate synchronization traffic for every register, or can you kind of, as an optimization, kind of basically aggregate all the synchronization traffic that is going between two switches?
I'm not sure I understand the question. Can you be more specific?
You were saying like if packets get lost, right? You'll have to send, broadcast, every now and then from, between switches. I was wondering if that happens kind of separately between different, like if you have like 3 registers, right, from 3 different programs. Do you do the broadcast like 3 different times at different periods, like periodically, or do you is there a possibility to kind of optimize by aggregating all of that?
Right. So you can basically aggregate all the updates in one packet. But the more limiting property of the switch is that you are limited to the number of memory locations that you can access per packet. So if you want, for example, to synchronize a more complex object like a sketch, then you won't be able to aggregate it efficiently. So if it's only a few registers, then I guess it's doable. But if it's a more complex data structure, it's going to be more challenging.
I see. Thank you.
Great. I think while other people are thinking of more questions, I had like a quick question. So I was curious, so you said like beyond NFs, like are there applications that require both like high consistency and like high write frequency? Like did you come across such applications
Yes, so there are many examples for that. I think I also showed them in my slide. One example is a network sequencer where you basically apply monotonically increasing sequence numbers to packets. So that is one example. Another example may be a key value store that has to be consistent. So yeah, there are many applications that might require both properties.
Which like SwitchMem can't currently support.
That's correct.
Okay, sounds good. So I think we're also running out of time, so maybe we can continue more discussions over Slack, and yeah, we can move on to the next speaker. Aditi, would you like to introduce the next speaker? Thank you, Leo.
Sure.
Thank you.
So the next paper that we have is titled Elastic Switch Programming with P4All. It will be presented by Mary Hogan, who is a third-year PhD student at Princeton, and she is advised by Professor Jennifer Rexford. She is broadly interested in programmable networks. So I guess we can get started.
Yeah, thank you for the introduction. So I'm Mary, and today I'll be talking to you about our work on elastic switch programming. So traditionally, data plane switches can sort of slow and hinder innovation because they have fixed components that can't easily be changed to support new protocols. And as an alternative, we now have protocol-independent switches. So these have configurable parsers and configurable tables that allow us to relatively easily reprogram the switch to support new protocols. So we use the programming language P4 to program these parsers and tables. So P4 programs can be as simple as just like a forwarding application, or it can be something more complicated like a telemetry application. So we argue that this P4 code really should be reusable. So we have a single P4 program, we run it through a compiler, and then ideally we can run it on a variety of different targets, each with different resources. And we shouldn't have to change the original P4 code. In reality, though, I'm sure most of you who have programmed with P4 know that this development process for P4 is much more complicated than this. And P4 code really isn't that reusable. So in particular, data structures that we might use for our application, things like Countman Sketch, are valid for a range of different sizes, but P4 requires us to give an explicit definition of their size. So things like the amount of memory it uses, logical tables, etc. And so this basically means that we have to adapt these P4 data structures to fit the very constrained resources of specific targets. And so for different applications and different targets, we're often rewriting these commonly used data structures. This basically gives us a circular development process where we have our P4 program, we try to compile it, and if it doesn't fit, we have to go back and keep rewriting it until ultimately it compiles and fits in our target. So our goal with P4All is to really mitigate this circularity, and we accomplish this by adding a small set of constructs to P4. So in particular, P4All streamlines the development process with elastic data structures that are reusable. These elastic data structures are defined by symbolic values, and their size stretches or shrinks based on the resources of the target. So in other words, the programmer doesn't have to explicitly define the size, and they don't have to just guess on what will fit on their switch. So because of this, we have a single P4All program that can compile to different targets without having to rewrite it. So before going into the details of P4All, I'm going to briefly go through a scenario that illustrates the circularity process that P4All aims to alleviate. So I know we had a great overview of PISA in Nadine's talk, so I'll just sort of briefly go through what the architecture looks like. In particular, I just want to point out that we have a packet processing pipeline that consists of a series of stages, each of which has a very limited set of resources. And these limited resources are often what makes P4 programming so difficult. So one potential data structure we might want to fit on this architecture is a Countman Sketch. So a Countman Sketch is a probabilistic data structure that uses multiple hash functions to keep approximate frequencies for a stream of items. So for this example, I'll be showing you a sketch with 3 rows and 4 columns. So suppose packet X comes into our switch. We can hash it to each of the 3 rows, and then we'll increment the count there. And then packet Y comes in, we do the same thing. And if we want to retrieve the count of a specific item, we take the minimum across each of the rows. So suppose we want to fit this Countman Sketch onto a PISA pipeline. And let's say we only have 3 stages that we can use. One way we can do this is by breaking up the sketch and putting a single row in each stage. Suppose we only have 2 stages, though. That means maybe we could only fit 2 rows. So we'd have to go back and rewrite our original P4 program to get rid of that 3rd row to make it fit within the 2 stages. So in my talk today, I'm going to go through what a Countman Sketch looks like in P4, and then I'll show you the same data structure in P4All, and I'll conclude by talking about some of our ongoing and future work. So first, I'm going to show you some code snippets of a Countman Sketch in P4. So in P4, we define each row of the sketch as a register array. So we have 3 register arrays here, which are the counters 1, 2, and 3. And then the number in parentheses, which is the instances, this represents the number of columns in our sketch. So we have 4 columns in our sketch, so we put 4 instances. We can also define some metadata fields that are associated with each packet and are carried with the packet across the pipeline. So for our sketch, we might want a field to represent the global minimum. And then we might have some fields to represent the index, which is the result of our hash function, and then the count stored at each row. And for this example, I'm only showing the values for 1 row, but it would essentially be repeated for the other 2 rows in our sketch. So then we can define some actions that we want to perform on the sketch. So the first one might be an action to update the row, which will hash the row and increment the value there. And then we might have an action to set the global minimum. And then in the apply block of our P4 code, we can invoke these actions. So we first invoke the action that updates the row. And then if the count at that row is less than the min, then we can set the global minimum. So this is basically sort of some snippets of what a count-min sketch looks like in P4. And now I'm going to show you how we can write the same data structure in P4all. So on the left is our P4 code, and the right is our P4all code. So in the P4 code, we explicitly define the 3 registers, each with 4 instances. And in P4all, we instead use symbolic values to represent the size of our sketch. So in particular, we have 2 values, one for the number of rows and one for the number of columns. We also allow programmers to use assume statements, which gives some bounds on the values that they want for a symbolic value. So instead of defining 3 separate register arrays for our rows in the sketch, in P4all, we define a symbolic array. Each item in the symbolic array is a row in our sketch, and then we can use our symbolic value to define the number of columns. We can also do the same thing for metadata, where we define a symbolic array for the metadata fields. So now that we've defined the elastic data structure, I'm going to show you what it looks like to define elastic operations on our data structure. So in the P4 code, we have this increment action that updates each row in the sketch, and we have 3 separate actions, one for each row. And in our P4all code, we only have a single action, but we add this extra parameter that we're calling an index. And this basically allows us to refer to different items in our symbolic array. And then in our apply block, when we invoke this action, we use a for loop whose number of iterations is bounded by a symbolic value, in this case, number of rows. And then in each iteration of our for loop, we invoke this increment action and we pass along this I variable to refer to a specific value in our symbolic array. So now that we've defined elastic operations, we just have one piece left, and this is a utility function. So the purpose of utility functions in P4all is to really help us find the optimal size of a data structure given the resource constraints of the target. So it essentially is a function of how well the data structure performs. In the case of count-min sketch, this might be the error of the sketch. And so ideally, we want to define the error in terms of the size. So I'm not going into too much detail about how we find this function, but I refer you to our paper if you're curious. But essentially, we can use this function to define the error in terms of the number of columns. So we can optimize this function to find the best number of columns for our sketch. One thing in particular I'll point out is we have this alpha variable, and this is a workload dependent parameter. So oftentimes the utility of a data structure can be workload dependent, but we assume for now that the user supplies values for any workload parameters in their function. So once we define the function, we include it in our P4all program using this optimized keyword. So now that we know what the P4all language looks like, I'm just going to conclude by talking about some ongoing and future work. So first, we'd like to better design representative utility functions. So in particular, it may be difficult for a user to come up with those mathematical formulas, or perhaps their application might not even have a well-defined formula for utility function. So we're currently working on how to make it easier to define these utility functions. And we'd also like to support dynamic utility functions. So in particular, for functions that have this workload-dependent parameter, we want to be able to adapt our utility function based on the workload that we're seeing. So we can get some feedback from the network and adjust our utility function so we can have the optimal size data structure. And lastly, we'd like to implement an object-oriented programming model. So in particular, we want to create a library of reusable modules for commonly used data structures. Thank you. And with that, I'd be happy to take questions.
Okay, thank you, Mary. That was a very interesting talk. So if there are any questions, feel free to raise your hand. Okay, so I think while people think of questions, so actually I was very curious about these utility functions, and you said that like it can be hard to define them. Like, can you elaborate a bit more on like what you are? So you said like this is something that you're working on currently. Like, do you mind sharing like how can you make it easier to specify utility functions? Like, do you have any thoughts on that?
Sure. So one thing that I think would be useful is instead of having the user basically say like, let's measure error in terms of like size, one thing that I think we can do is just say, to have the user give us one metric that they want to optimize. And then on our end, maybe run some simulations with different workloads and different sizes of data structures and do some simulations to pick the optimal size without the user having to define a specific formula.
Okay, so, but this would still, like in the sense, like you would still need like some representative class of utility functions for which you could run the simulation. So like kind of mapping like user program to some like classes for which you could run simulation. In the sense like it's like the program could be arbitrary in the sense these utility functions could be arbitrary in some sense. So yeah, so basically, yeah, I'm still kind of curious about that. But anyways, I think I can ask more offline. But Anup has a question. So I'll unmute Anup. Anup, you can.
Hi, am I audible?
Yeah.
Hi, great talk. So your talk basically talked about one particular source of hindrance to reusability of P4 code with respect to elasticity in data structures. I guess another source that hinders reuse of P4 code is that different targets will expose different functionality, which could be, let's say, through black box functions, or they could be through like some targets will allow you to implement functionality using micro C. And then like as a programmer for this infrastructure, like you'll have to then have separate code which aims for each target. Is there something that you've thought of that can be done to mitigate this kind of hindrance to P4 code reuse?
Oh, thank you for the great question. That's really great. Yeah, I think this is something that we're still struggling with. I mean, most of our experiments have been specific to Tofino, but we know that, you know, Tofino obviously doesn't generalize to all different switches. So I think that's definitely still an open question. But yeah, it's definitely worth thinking about, but we haven't, something we're still grappling with and we don't really have a great answer for.
Okay. Yeah, it actually is a important problem because everyone faces it. Yeah.
All right. Thank you, Anup. So we can continue the discussion further over Slack if there aren't any more questions right now. Thank you for the great talk, Mary. And I think we'll move over to the next speaker. Okay, so our next talk is on enabling active networking on programmable switches. So this talk will be presented by Rajdeep Das, who is a PhD student in CS at UC San Diego, where he's advised by Alex Nurin, and his work focuses on in-network functionality using programmable switches. So Rajdeep, you can take it over. Please share your screen and turn on your video and audio.
Yes, just a second. Yeah, so thank you for the introduction. So this is Rajdeep, and I will be presenting enabling active networking on RMT hardware. Now, there's always been a desire for deploying application functionality over the network, and this is usually done through middle boxes and network accelerators. Now, recent trends have, however, changed, recent technologies have, however, changed the mode of deployment to be much more efficient in terms of both cost and performance. And I'm specifically talking about programmable switches. So in a typical usage scenario, a programmer writes a program in a language called P4, compiles and loads the program onto a programmable switch. Now, when the switch receives packets, it executes this program on those packets, thus achieving certain network behavior. Now, the limited computation and storage on these devices actually enable implementing a wide range of functionality. In fact, in recent times, we have seen a number of applications being built on top of these devices. These devices have indeed been very good at supporting a large number of applications. But when we think of deploying these applications in, for example, cloud providers and enterprise networks, we need to change the way we deploy functionality over programmable switches. Now, this is because in the usual mode of operation, programmable switches have several drawbacks. Especially when we want multiple programs to run at the same time. Now, deploying a new network function involves writing a P4 program and loading it onto the switch. This requires intervention from network operators, which is a hassle in terms of deployability. Also, P4 switch cannot run multiple P4 programs, so multi-tenancy is not really supported naturally. The only way to do this is to superimpose multiple programs into one big program and then compile and load it onto the switch. But even then, once compiled, the resources allocated to these individual subprograms, as you may call it, cannot be altered at runtime. Now, we have a solution to all these problems. So if an application wants the network to behave in a certain way, then it can encode that behavior into network packets and then have the switch execute that behavior. Now, this is something that we have all heard before, right? And this is active networking. Now, active networking only solves one part of the problem, though. So if we want to ensure multi-tenancy, we have to find a way to partition the switch resources among multiple applications. So in other words, we have to virtualize the switch to the console and multiple active programs can run on them. So we combine these two ideas into a system targeted specifically for programmable switches based on the RMT architecture. So for those of you who are not familiar with RMT, it consists of pipelines that begin with a set of programmable parsers, followed by a series of match action stages, as was described in some of the previous talks. Now, each match action unit has ALUs and stateful memory in the form of SRAM that can be used to persist information across packets. Now, on top of this programmable switch, we have written a runtime using the P4 language, and that runtime exports abstractions for ALU registers and stateful memory. So these abstractions are also exposed to the active programs through an instruction set architecture, and we'll catch a glimpse of that in a bit. In addition, we also have a resource manager whose job is to allocate and partition resources, such as memory, among different applications. So let's go a bit deeper into this thing. So a program is encoded as a series of instruction blocks following a special header, I'll call the program a header in this scenario. The programmable parser collects the instructions from the packet into an internal data structure, and then the match action stages execute each instruction one per stage. Now, since the number of stages on a switch are limited, longer programs require the packet to be recirculated back into the pipeline at the cost of bandwidth. So let's walk through an example application. Let's take a popular application people have proposed in the past, which is a key value store. So a client sends a read request to a backend key value store using an active packet, and the key value store appropriately responds with the requested object. Now let's introduce our M2 switch running a P4 program corresponding to the caching program. We can use an example such as netcache, which was proposed in the past. So let's assume that the cache is already pre-populated with objects. So now when the client sends read request to the backend key value store, the switch intercepts the packet and executes the P4 program corresponding to the cache. The P4 program then checks whether the requested object is cached on its local storage or not, and if it is, then the object is written to the original packet and returned back to the sender. Okay, now things get a bit more interesting when an active program is used. So the switch, upon receiving the packet, instead of running the functionality defined by the P4 program, now runs the functionality encoded in the active program, or the functionality encoded in the packet itself, which then returns the object from the cache if present. Now here's the corresponding active program for an example like this. We could have a separate shorter active program that can be used to write objects to the cache, but we omit it over here due to time constraints. So the first four lines of this program, the key corresponding to an object is loaded into an internal variable, then to obtain a virtual address. Then that then the virtual address is translated into a valid memory location that can be accessed by the application. Then a memory read is performed to fetch the actual object. If the read is successful, then the conditional jump instruction or the cjump instruction enables execution of the next two instructions, which load the value of the object into the packet and then marks the packet for returning back to the sender. else the packet is forwarded as usual to its original destination. Now, in practice, we would want more complex functionality to be expressed using our system, so we designed a preliminary instruction set architecture that supports constructs that enable operations such as arithmetic logic operations, hashing, then control flows such as branching and loops, and even direct and associative memory access. Now, some examples of full-blown applications that we implemented using this instruction set include an object cache, such as the one we described before, but a full-blown version of it, including features such as hot item monitoring, using Cogman Sketch and so on, and even randomized entry aging. Then we also implemented a load balancer with dynamic DIP pools and even simple database joins. So our instruction set is indeed expressive enough to encode complex functionality. But as we continue to explore and implement more applications, we need to concern ourselves with challenges such as resource management, and one of which is memory. Now, on-chip SRAM is scarce on switches and needs to be shared among multiple applications, right? So for this reason, we have a mechanism for performing dynamic memory allocation. So whenever the set of applications using the switch memory changes, the controller performs a reallocation. There are, of course, various policies that could be used for reallocation, but we have currently experimented with an equal allocation policy where the existing memory space is split equally among all the applications. Now, however, in practice, different apps benefit differently from equal proportions of memory. So the figure on the right shows how performance changes with memory allocation changes for a load balancer. The performance metrics normalized by the worst case performance, which is in this case, the number of broken connections. So the lower the bar, the better. The x-axis shows the amount of memory allocated. So it's like 1 block of memory, 2 blocks of memory, 3 blocks of memory, and so on. So, so a higher bar, as I said, represents worse performance, and a lower bar represents better performance. So we now show a cache with similar allocation changes. So in the case of cache, the metric corresponds to the response latency normalized by the worst case. But even in this case, the lower the bar, the better. This shows that a load balancer benefits much more than a cache used in the previous examples when more memory is allocated to it. Now, this is because the number of connections that a load balancer can store is linearly proportional to the amount of memory it has. And now this is unlike the cache, which is sublinear. And so it makes sense more to reallocate to the load balancer to get better overall performance. Now, some standard challenges from active networking need to be addressed when we go about designing the system. So we first need to address some security concerns, such as verifying whether the active program that is going to be executed can be trusted or not. Now, another thing to note is that expanding headers to include programs reduces the network throughput. But the good news is that solutions to these problems already exist in some form of earlier academic work. So we can always borrow these ideas and incorporate them here. Now, as we use newer devices, there are additional challenges that need to be addressed. And as we mentioned earlier, longer programs may require packet recirculation. And this consumes additional bandwidth, which has accumulating effects even if the packets are recirculated just once. But given that bandwidth is cheap in data centers, it makes sense to allocate surplus bandwidth towards in-network computation. So we can also think of ways to reduce the length of active programs so that more programs can fit within a single pass through the switch. In its current state, our runtime executes one instruction per stage. And this is kind of suboptimal for several programs which could otherwise be compiled in MP4 in a much more efficient way. So we need to design a way to take advantage of the switch pipelines to be able to execute mutually exclusive instructions concurrently. Now, this is not an exhaustive list of challenges that need to be tackled, and we do expect to find a lot more as we keep on building the system. So in fact, I'm also looking forward to additional feedback that can help reveal some more challenges. So with that, I will conclude my talk and open up for questions. So thanks for listening.
Thank you, Rajdeep. That was very interesting. Yeah, if there are any questions, please raise your hands. Okay. So I had like a quick question, Rajdeep, before others get a chance to ask. Can you tell a bit more about the limitations of the programming model? Like basically, like, is it possible to encode any arbitrary P4 program in packet headers? Like, are the limitations on the size of the program in terms of like how big the packet could be? Or is the key limitation mostly just like parsing the instructions and executing them, which may require some sort of recirculation? Like, what are some of the constraints that could limit the programmability, and what are those limits?
Right. So that's a great question. The size of the program is limited by the size of the packet itself.
Mm-hmm.
So for a standard 1500 byte MTU sized packet, you could fit around a program of around 300 instructions. Now, most of the programs, the longest program that we have written so far is around 55 instructions. So that can still, so 300 instructions is a pretty large program.
Mm-hmm.
But yes, as I mentioned before, programs that are longer need to be recirculated back into the pipeline. And as other people have mentioned before, this costs network bandwidth. So although it is technically possible to do that, it may not be ideal because of performance degradation.
Okay, great. I had so just a quick follow up on that. So what was the longest? So you said like the longest program was like 55 instructions. Do you mind sharing like which program it was, like amongst the ones you tried? Like, I'm just curious.
So it was an object cache request program. So the program would check if an object exists on the cache and then return the value. We would also perform a count sketch algorithm to track the frequency of objects, and mark items as hot items if it surpasses a particular frequency.
So just to answer your framework, so this piece of code must be sent with like every request to the key value store, or is it something that just like a few programs carry, and like the switch can cache these instructions and reuse them across multiple packets?
Yeah, so as of now, every packet needs to carry the program. So we are working on a way to cache this on the switch because it obviously reduces network throughput. It's not the best, it's not the most efficient. But yes, that is something we are working on. But right now, every packet has to carry the active program.
Okay, great. I think we can continue more discussion over Slack if there aren't any more live questions. So thank you, Rajdeep. I think with this, we are done with our session, and I think we can move over to breakout rooms now. Thank you. Thanks.
If my clock is right, then it's time to begin. Welcome to the last session at HotNets. This is aptly called Edge and Space because there are papers on Edge DNS and there are like 3 papers on space. So this is going to be a very, very exciting session. I'm Aruna Balasubramanian. I'm a faculty at Stony Brook, and I'm going to be co-chairing this session with Akshay. Just a reminder before I hand it over to Akshay, that for the audience, if you have questions, you can raise your hands and I will unmute you. You can ask the questions. If not, you can type on the Slack channel. Each paper has its own Slack channel. I'm sure you've seen this. You know the drill by now. This is the last session. So let's take it away, Akshay.
Thanks, Aruna. Hi, I'm Akshay Gadre. I'm a 4th-year PhD student at Carnegie Mellon. I'm a wireless communications and mobile systems researcher, and many would have seen our paper on full duplex radios yesterday in the wireless session. However, today's session is about edge and space. So let's get this show rolling. So our first speaker is Nitinder Mohan. He's a postdoc researcher at Technical University Munich, Germany. He completed his PhD at University of Helsinki, Finland on enabling protocols and platforms for edge computing. Today, he will discuss several hyped assumptions that exist within the community regarding capabilities of edge computing. He's here to present his paper, Pruning Edge Research with Latency Shares. Over to you, Nitinder.
Hi, can you listen to me?
Yes.
Can you hear me fine? Okay, great, awesome. Thanks for the introduction. So hello, everybody. I'm Nitinder Mohan, and today I will be talking about our work, Pruning Edge Research with Latency Shares. This work is done in collaboration with folks from Uppsala University, Sweden, University of Twente, Netherlands, and University of Helsinki, Finland. In this talk, I will discuss the overview and importance of edge computing research, and I will try to showcase several assumptions that the research community falsely makes about the field sometimes. So before we start to discuss edge computing, we need to understand where the field arose from first. The figure shows a typical configuration of a cloud computing environment. The cloud can be viewed as a centralized large-scale deployment of data centers to which different users and applications can connect to from different parts of the geographical region. Cloud was a huge success since its inception, as the type and the volume of the application's resources could be elastically adjusted to meet the demand on fly. Since the data center farms are carefully managed and controlled, the cloud boasts of a high level of reliability that allows applications to scale their reach globally. Edge computing came to the scene in about 2009 with a Cloudlets paper from Professor Satyanarayanan. The idea behind the edge computing was quite simple. Decentralize the cloud computing environment and put compute services closer to the user. The primary motivation surrounding the research was the large latencies that the user had to encounter to connect to the cloud data center. The idea started with deploying managed mini data centers and infrastructure closer to the user, but soon spread like wildfire with many proposals pushing computations to the smartphones, routers, and even IoT actuators. The need to push the envelope further and further was justified by the fact that the compute requirements were no longer limited to traditional client-serving applications, but was being driven by next-generation applications, the likes of AR, VR, autonomous vehicles, etc. And unlike users, these applications impose strict latency and bandwidth demands that the current cloud environment does not really satisfy. So before we proceed further, let's first try to understand what are these next-generation applications that are driving the hype around edge computing and what requirements do they really impose. We analyze the existing publications on the subject and categorize next-generation applications based on their latency bandwidth requirements. The y-axis here shows the required latency, which can range from a few milliseconds to an hour, and the x-axis shows the amount of data that an application usually generates. We found the majority of applications are human-centric in nature and are therefore governed by absolute human vestibular thresholds. The most stringent threshold is known as the motion to photon latency, which is the delay between the user input and its effect to be reflected on the display screen. MTP latencies are estimated to be around 7 to 10 milliseconds and can result in motion sickness and dizziness if they're not adhered to. Maintaining latency below MTP is critical for immersive applications such as augmented reality, virtual reality, etc. The second latency threshold is the perceivable latency, which exceeds when the delay between the user input and the visual feedback becomes large enough to be detected by the human eye. PL threshold is estimated to be around 80 to 100 milliseconds and is critical for immersive interactive applications like cloud gaming. The final threshold is the human reaction time. It is the delay between the presentation of a stimulus and the associated motor response by the human. HRT threshold is often estimated to be around 250 milliseconds and is required for applications that have active human engagement like remote surgery. So it now becomes easy for us to place all the next generation applications on the latency bandwidth graph here. The form and the orientation of the application represents the strictness it poses towards the latency and bandwidth constraints. The application color denotes the expected market share by 2025 in US dollars, which is taken from internet sources. Based on the similarities, the applications can be broadly divided to really 4 quadrants. Quadrant 1 here on the bottom left encompasses the applications that require low latency for operation but generate quite low data. Quadrant 2 holds applications that generate both large volumes of data and impose strict latency constraint. Most of the hype applications for edge computing, like autonomous vehicles, fall in this quadrant. Quadrant 3 on top right is composed of applications that generate large volume of data but have very relaxed timing constraints. And finally, quadrant 4 on top left comprises of applications that neither generate large volumes of data nor require strict latency for operation. Now that we have quantized the requirements of next generation applications, we can ask ourselves the questions: can the current cloud infrastructure really not support the requirements of these applications? Our curiosity stems from the fact that the state of cloud computing infrastructure has changed significantly over the past 10 years, with many more cloud providers entering the market and big providers like Microsoft and Amazon expanding their existing infrastructure to more geographical regions. On the other hand, almost a decade has passed since edge computing was introduced in the research community, and yet we do not see any large-scale deployments to support its operational claims. To this end, we reevaluate the latency-centric claims of edge computing with extensive global wide area measurements to data centers of major cloud providers. We targeted 101 cloud regions from 7 major cloud providers, as shown in the figure, which have significant global coverage. We explicitly selected to target regions which offer compute capabilities and install a virtual machine as an endpoint. Our selection gives us a good mix of providers that have deployed their own low latency network backbones with wide-scale ISP peering versus those who rely on public network infrastructure for interconnecting their data centers. For our vantage point, we rely on Atlas, which is considered to be the de facto platform in the internet measurements research community. Atlas probes are installed in varying network environments and allow us to analyze user reachability to the cloud globally. We use 3,200 plus probes distributed in 166 countries, which we get after filtering out probes that are clearly installed in privileged locations, for example, in data centers and ISP infrastructure. For our experiments, we measure end-to-end latencies between the probes and the data centers by ISP pings that repeats every 2 hours. All the measurements have been ongoing since September 2019, and in this work, we draw results from 9 months of data collection. Our dataset spanning several gigabytes is available for public use as well. Please refer to the paper or at the end of the talk for the link. So the first question that we answered with the measurements is the spread of the cloud across the globe in terms of latency. The plot here shows the minimum ping latency observed by the best performing probe for every country to any cloud data center. The red diamonds here denote the locations of the cloud regions that we target in our measurements. Firstly, we can observe that a total of 32 countries can access the cloud in less than 10 milliseconds, and 21 countries can access it within 10 to 20 milliseconds. Together, these countries form 70% of the world population, showcasing the effects of immense growth of the cloud infrastructure. The reasons for low latency becomes clearer when you correlate them with the deployment of data centers as well. 80% of the probes, for example, in Europe and North America, which have the densest cloud deployment, and they also equate to the 50% of the total probes we use in approximately our measurements, can access the cloud within 20 milliseconds. The latencies are a bit longer in continents with the low availability of the cloud. Despite that, we find that about 75% of the probes in Africa and Latin America can access the cloud within 100 milliseconds. And in total, 80% of the probes globally could reach the cloud within the perceivable latency bounds, which was 100 milliseconds. Almost every probe, except a few in Africa, could reach the cloud within the human reaction threshold as well. While in this presentation, we only cover a subset of the results, I encourage you to refer to our paper for a more detailed analysis. But all this looks very fine and dandy, and it might lead us to another question. Where is the latency in all this? So for this, we show the CDF above, which has the latency distributions for all the measurements from all the probes, which are grouped by continents. We also mark the latency thresholds for the next generation applications for correlation here. Despite the extensive reach of the clouds, the result indicates that only a fraction of the probes in Europe and North America can consistently reach the cloud within 10 milliseconds latency as required by the motion to photon-based applications. For continents with dense cloud deployment like Europe, North America, and Oceania, it is largely possible to reach the cloud within 100 milliseconds and support applications like cloud gaming. For Latin America, Asia, and Africa, cloud reachability is actually quite poor, and only a fraction of probes can satisfy the perceivable latency threshold here. Probes in Asia show much diverse latency due to the scattered and clustered data center deployments, favoring a few countries like India, China, Korea, etc. We observe the worst performance in Africa, since it is severely underserved both in cloud presence and network infrastructure. Another major cause of the long latency to the cloud can be due to the wireless last mile. Many studies in the recent past have shown that the wireless medium in both cellular and Wi-Fi is the main primary bottleneck due to frequent packet drops, handovers, etc. To investigate this in our measurements, we filter out probes that the user tagged as wired connections, for example, Ethernet, broadband, etc., and the probes which are tagged with wireless keywords. Further, we filtered out probes that were deployed in similar regions for both sets and plot their latency towards the closest data center. It is evident from the block spot shown here that the probes tagged with wireless perform considerably worse than the wired counterparts, often taking 2.5 times longer to access to the nearest cloud region. Our result is in line with the other recently published measurements that show that the users can experience 10 to 40 milliseconds added latencies when they're using a wireless last mile. In fact, a recently published study from Nokia Bell Lab shows that the latency gains to connect to an edge server closer at the closest LTE base station is minimal compared to a cloud data center located 1,000 kilometers away. New technologies like 5G promise much shorter latencies, but recent investigations really show otherwise. Learning from our observation, we can now revisit the next generation application requirements and plot the regions of edge reality here. The latency feasibility zone of edge computing is shown in red. The lower bound of the zone is placed at 10 milliseconds, which through ours and previous analysis in the area is the average wireless last mile access latency. Even if the edge server is placed at the nearest base station, it would still take about 10 milliseconds for a user to reach it, and thereby making the MTP threshold unachievable. The upper bound is the human reaction time, which, as we observe from our result, is the time with which almost every region around the globe can reach the cloud. The region in the blue here shows the bandwidth feasibility zone of edge computing. Edge is most useful for applications that generate enough data to congest the network. Specifically, benefits from the edge are greatest closer to the user and decrease with increasing distance and can be further affected by the contention of the wireless last mile. Based on the previous studies, we estimate approximately 1 GB per entity data generation to be the lower limit for bandwidth threshold. The overlap of the two feasibility zones here gives the edge computing operating reality to us. The applications in this zone clearly benefit from the deployment of the edge, as they benefit in both latency and bandwidth. Interestingly, many hyped applications that are used to motivate the need for edge computing do not really fall in this zone, either because their requirements are too strict or they're too relaxed. Moreover, the predicted market share of the applications within the feasibility zone pales in comparison to those for which edge do not really provide much benefit. But does this mean we're heralding the end of edge computing here? Not really. Our aim in this work is to showcase that in light of the recent trends in cloud computing, the reduction in latency argument no longer holds true for the edge. However, we want to stress that the latency argument is just the only single piece of the puzzle, and there are other considerations that are more convincing drivers for edge. For example, the inherent privacy that the edge provides by decoupling the applications like benefits of the edge can be many in this regards. We identify several promising directions for future research in edge computing domains for which you can refer to our paper for more insights. With that, I conclude my talk. You can find our data set from the link shown here. If you have any further questions, I'll be really happy to answer them. Thank you.
Okay, that was a great talk. I really enjoyed it. I think Ethan has been wanting to ask a question for a while. So,
Hi. Can you hear me, everyone?
Yeah, I can hear you.
Great. Thanks. I really like the work and I like the questions that you're asking. And I think that the application matrix that you have is a really nice way of structuring the question. I was trying to understand a little bit about interpreting the results. So the latency thresholds that you have in that matrix are for application messages, which might include overhead beyond a single network layer ping. And also they're for applications that often serve wireless clients. And you're measuring network latency with ping from mainly wired vantage points, and ripe atlas coverage tends to be biased towards better connected networks and regions. So I was trying to understand how to translate your results for these network layer measurements from ripe atlas to conclusions about application layer latency for mainly wireless users. And you had the one slide touching on wireless, but I'm not sure I totally got the details of how to translate all of this.
Sure. Yeah, thanks for the question. So I'll take this in two parts here. So number one is that how do we translate our results to a more realistic application setting? So the current results that we show here is majorly from ICMP pings, which as the reviewers and also we also figured out that it's not really reflecting the real application performance here. So from that point onwards, we also started to do TCP pings to get some idea, and the results are quite surprising. I have a few slides to show here. Let me find them out, actually. Just give me a second. No,
but while you're at it, it's not just TCP, right? If it's an application, you probably have to do a few round trips, which may also matter.
Sure, exactly. Just give me a second. Let's see if this works. All right, can you see the slide?
Yeah.
Yeah, okay. So TCP pigs kind of give us a little bit more idea, because now at least we can be sure that these are end-to-ends, right? So with the ICMP, this is also kind of in the community known that your middle boxes are interacting with the traffic and you are not really measuring end-to-end data. So the first thing we wanted to figure out was that how much do these TCP or end-to-end latencies differ from the ICMP latencies? And the results here were a bit surprising to us. So consistently across the board for cloud measurements, we found that the TCP latencies were much shorter than your ICMP latencies. And this is just across different regions. And then these are a couple of plots that I have. These are also pre-production qualities here. But we see that consistently across the board, your TCP gets some lower latency numbers. The point about actual application traffic and what kind of latencies do they get. This is something that we have been also thinking about how to measure exactly. We don't have a really good idea because they can vary in different kind of bandwidth requirements as well. And it's very difficult to simulate an actual application working unless and until you have that application working, right? So across the board in a generalized measurement method, we don't have good answers so far, but I'm really looking for some good feedback across this session to get something.
Yeah, a simple. Oh, sorry, Aruna.
Go ahead.
No, a simple starting point might just be for the applications that you already have in the matrix, think something about what the overhead is for those specific ones, so that you could have a kind of translate an application overhead into a per round trip latency threshold that you would need for that particular application. That might be a starting point.
Sure.
I agree. It's difficult to do it in a generalizable way.
Yeah, definitely.
And then what about if other people have questions, feel free to jump away from me. But I'm curious about the other parts, the kind of coverage of RIPE Atlas and limitations of that, and then if you have more to say about the wireless versus wired.
Sure. So RIPE Atlas is definitely a very biased platform. So to get more variability into our measurements, we also shifted our measurements to including other platforms here. So currently we're looking at Speed Checker, which is mostly wireless probes, and you can essentially do the similar kinds of measurement performances that you do on RIPE Atlas as well. But the results on those are still, I would say, under the cooker. I don't have anything to show as of right now, and how do they differ from the results from our RIPE Atlas, but maybe in a future paper, but stay tuned.
There's also some interesting discussions I see on Slack you might want to follow up on. There aren't any questions, but more in the lines of what Ethan was asking. And also, I also found it very interesting that this whole latency argument seems to, at least for a large fraction of users, seem to go away. I also had this question, actually, we're running out of time. Maybe we'll continue this on Slack. So I'm going to close this session and go back to Akshay, who's going to introduce the next speaker. Thank you very much, Nitin.
Yes, definitely a lot of discussion happening on Slack here. So let me introduce our second paper. The next paper will be presented by Deepak Vashisht. He's a researcher at Microsoft currently and soon to be an assistant professor in CS at QIUC. He works in the broad area of wireless networks and Internet of Things, and he's looking for future graduate students. He's here today to present his work on a geo-distributed ground station network for low Earth orbit satellites. Over to you, Deepak.
Thank you, Akshay. Hi, everyone. I am Deepak from Microsoft, and today I will talk about a new way to download large amounts of data from satellites using a new ground station design. This is joint work with Ranveer Chandra. In the last few years, we've seen a lot of growth in the satellite launches and proposals for satellite launches. And this is because of two reasons. A, low cost of building CubeSats, which are like tiny satellites that can be built for tens of thousands of dollars. And B, the low cost of launching them in low Earth orbits called LEO orbits, which are around 500 miles above the Earth's surface. So overall, you can launch satellites today for a few hundreds of thousands of dollars, as opposed to tens of millions that you would need in the past. And these satellites really have multiple use cases. For example, you have heard of satellite internet by Starlink or Amazon, and entertainment by Dish TV, etc. But a big chunk of these satellites, about 45% of LEO satellites today, is for Earth observation alone. And these satellites take images of the Earth and send them back to ground stations on Earth. And you can think of them like drones in the sky. These images are high resolution because of their low orbits. They offer high revisit rates, Because they have low orbits, they can travel faster, and you can also have multiple of them to give you a good revisit rate. And they also can use multispectral imagery like RF, infrared, RGB by just putting a different sensor on them. But the key challenge for Earth observation satellites is data downlink. They collect hundreds of gigabytes of data in every orbit. And for a ground station on Earth, they only have a span of about 10 minutes to get this data because of their low orbits, these satellites are not constantly in touch. So think about this. You need to send hundreds of gigabytes of data in just 10 minutes over a link that is 500 to 1,000 miles long. Clearly, this is very challenging. And today, this problem is solved by building massive ground stations with huge antennas and very high quality RF components. This costs millions of dollars to deploy. This makes sense though, because you need every last bit of SNR that you can get. Typically, large companies will deploy 4 or 5 such ground stations close to the poles. But the problem with this design is that this is really hard to scale. It is okay if you have 10 or 20 satellites, but if your constellation starts scaling beyond that, you're bound to suffer contention at the ground station. It also has large latency. Each orbit is around 100 minutes, so your latency is very high. And in fact, every orbit is not usable because different orbits pass at different elevations. So for especially important applications which are latency sensitive, like forest fires, etc., you might have to wait a few hours before you get access to your data. And finally, these ground stations are single points of failure. If you miss one download because of bad weather or faulty hardware, you lose your chance to access this data. So clearly, as we demand more from these satellites and we deploy more of them, we need a better solution to get the data from them. Our idea is to augment the existing ground stations with a network of many tiny ground stations. These ground stations are low cost and low complexity. They can be managed by independent operators or cloud providers. And many of these ground stations, more interestingly, are just receive only. We observe that most of the traffic on these satellites is download. We have to get the data down. The uplink is just some few kilobytes of telemetry data. So we don't need to equip all of them with transmit equipment. And it also avoids complex licensing procedures because we are not transmitting any data at all. And it makes these ground stations really easy to deploy. So think of replacing these huge dishes that I showed you earlier on the left here with the tiny dishes on rooftops. This makes the design more scalable. It reduces latency. You can always find a ground station to download your data to, and it makes it more fault tolerant. If the weather is bad in one part of the world, you can just use a ground station in a different part of the world to download your data. And on a high level, this is how the system would operate. So there is a satellite that's in contact with one of these big ground stations. It gets some information from the ground station about where to go and download its data. And as it goes in its orbit, it knows where the receive-only ground stations are. It can just transmit its data to them as it goes forward. And this data can then be sent to the cloud or this big ground station for further processing. Of course, this design leads to many technical questions, and I'll discuss some of these here. For example, how do we schedule satellite ground station links? How do we do data adaptation without feedback because our ground stations are now receive only? And how to deal with lack of acknowledgements? And that's what I'm going to talk about in the next few slides. So in a network of this scale, obviously, there are going to be many cases when you have multiple satellites in contact with the same ground station, or when you have multiple ground stations in contact with the same satellite. Which links do we pick? We can denote this problem as a graph where the value of each graph can be defined using this function phi, and it can denote latency, throughput, geographical restrictions, or your metric of choice. For example, a satellite from one country may not want to downlink data in a different country. This becomes, at the end of the day, a bipartite graph matching problem where you need to match ground stations to satellites. And we can solve this problem using the stable matching algorithm. There are standard solutions to that. We use the Gale-Shapley algorithm, and it converges in order k-square, where k is the maximum of the number of satellites and number of ground stations. And it ensures stable matching. And what we mean by stable matching is that no satellite ground station pair can find a better deal than what the algorithm offers it. The second challenge is rate adaptation. So the link quality between a satellite and a ground station can vary by up to 20 dB, but we are not getting any feedback from the ground station. So how do we decide what is the right rate to transmit this data? Because typically you would do this based on feedback from the ground station, but now that you don't have it, there is a risk. If you transmit at too low of a data rate, you waste an opportunity to transmit too much data. And if you transmit at too high of a data rate, you lose all of your information. So we need to find a way to do rate adaptation without getting any feedback from the ground station. So to solve this problem, we algorithmically estimate the quality of the link. And we do this in 3 steps. First, we estimate the orbit of the satellite using orbit descriptors, and you can do this pretty much a day in advance. And we use it to compute the elevation and the distance between the satellite and the ground station and model that loss. Then we estimate the loss caused by weather through weather forecasts. And finally, we calibrate for hardware losses on each of the ground stations. And together it will give us a sense of what's the link quality like, and we can sum these losses up and get an estimate of the ideal and optimal data rate to transmit this data at. Of course, even with our best estimates, the satellite will lose some packets, and it happens even in today's systems. How would the satellite know what data has been successfully downloaded if it cannot receive ACKs from the receive-only stations? So to solve this problem on a high level, this is what we do. We relay the data from the small ground stations to these transmit-capable stations. And later, when the satellite is in contact with this transmit-capable station, it can relay this information back to the satellite so that in the next round, the satellite can resend the data that has been lost. So this way, we can relay these ACKs through these transmit-capable stations with some delay. So I talked to you about the high-level ideas in our paper. I'll just briefly describe some experiments. We use ground stations in the SAT-NOX open source ground station network for our evaluation. So these ground stations are like small ground stations managed by amateur radio operators and hobbyists. And in our design, we get data from 259 satellites and 173 ground stations. But these ground stations operate at a lower frequency, around like 1 to 2 gigahertz, but real data downlink happens in the X-band, which is around 8 to 10 gigahertz. So we emulate the link there, and we emulate a download of around 100 gigabytes of data per satellite per day. And for baseline, we use 5 ground stations, which are high complexity. There are these massive ground stations that I talked about. And each of these ground stations has at least 10 times higher throughput than the ground station that we have in our distributed ground station design. So I'll just talk about 2 results. The first result is data backlog. That is how much data is not downloaded at the end of each day. And in this plot, the x-axis is the backlog, and the y-axis is the CDF. And this is the curve for the baseline, and this is for DGS. So on average, actually for both the median and the 90th percentile, we get 5 times lower backlog or 5 times better performance for DGS, which is the distributed ground station design that I talked to you about, than as compared to the baseline. And in fact, we did something better. We reduced the number of ground stations by 4 times. That is, we reduced the number of ground stations in our network to 25%. And by doing that, we reduced the overall capacity of the system lower than the baseline. So it means that this is now an apples-to-apples comparison. The overall capacity for us is the same as the baseline with those 5 stations. And even with that, our performance is way better. And this shows that some of the gains in our network are coming from geographical diversity alone. And similarly, our system DGS provides a much lower latency for data download. And I'm going to plot the latency on the x-axis, and the y-axis is the CDF. And by latency, I mean the time that it takes from data capture to data delivery on a ground station. And I'll again compare the baseline with DGS and DGS 25%. So this is the curve for the baseline, and this is for DGS. The median latency goes down from 58 minutes to just 12 minutes. And this is very important, as I said before, for latency-sensitive applications, for example, disaster management and controlling forest fires. And even with DGS 25%, the latency is pretty low. Finally, this design is in no way complete. We think of this design as a baseline, which all of us can build on. And we want to start a conversation around this alternative form of ground station designs in the community. So there are a lot of open questions, and some of which I'll point out here. So the first question is around satellite power. So if you think about it, now that the satellite can talk to any ground station on Earth, it has to keep its radio on for longer. So how do you manage power on the satellite with a radio that's on for longer? The second question is around the economic model. Who is managing these ground stations? How are they getting paid? how do we make sure that the data access there is secure, and how does this data eventually end up with customers? Then there is the question of edge compute. So of late, there has been some work in this low Earth orbit satellite community where we talk about doing edge compute on the satellite itself, so that we reduce the data that is sent on the downlink. We believe that's not the right model, because for a company that manages these satellites, the money is coming from the data, so that you don't want to be discarding any data a priori on the satellite itself. But what you can do is you can have edge compute closer to these tiny ground stations, so that you can prioritize some kinds of data transfer and have storage co-located on the ground station. And finally, as a last point, in this talk and in this paper, what we focus on is point-to-point link between a satellite and ground station. There is some new ground station designs which are not commercial yet, which can beamform to multiple satellites at the same time. And if you can use them, then of course the optimization problems that we talked about become different. So to conclude, I think there is a lot of exciting work going on in this space. I would love for you to check out what Microsoft is doing here on aka.ms/Azure Space. And thank you. I'm happy to take questions.
Thank you. That was very interesting. So let me quickly see if there are any questions. So until somebody asks some, I have a few questions. I don't know if I missed this, but what communication platform are you using for the actual communication, both in the case of these large ones as well as the smaller ones?
Yeah. So there is like our evaluation is in part emulation and in part like real data, and the real data is coming from SatNox. So this is an open source. It's basically a community-based open source network where like multiple people are deploying it. And the typical way to do this is using like software-defined radios and use satellites that broadcast their data. So these are not like private satellites; these are public satellites that broadcast their data, and they measure like SNR and get like just download the data. And that's the data that we're using for say like computing orbits and all of that stuff. But the actual link, we are still like emulating it, because the actual link happens at much higher frequencies than where these ground stations are at. And that one is around like 10 to 20 gigahertz. So we don't have that data yet.
I see.
Or at least not in this version of the paper.
But I think my question stems from the fact that like I can see the diversity in terms of geography, right? Because you have more. But why would the cost of these other base stations be smaller? Or how? What do you think is the ratio between the cost?
Yeah. I think that's a very good point. So the way to think about this is that so there are two reasons why the cost is smaller. One is that like the system itself is smaller. Like the dish antenna you use is smaller. It is lower quality, because you don't need like as high of an SNR. And the second reason is that they are the same only. So the licensing costs are much lower. Like you don't have to license like transmit capabilities in every location that you go to. So these are like two ways to think about the cost. And I think in general, like the broad like idea here is that like, so you have these ground stations today, but you have to either keep increasing their capacity or make them more distributed. So we're proposing a design that makes them more distributed and see how that plays out so that we can advocate for it.
I see. I also have, I think, since I have the floor, I might as well. My last question is like, what kind of application protocols do you think you should be using, or do you think everything should be just done at the link layer so that you don't have to worry about any of these overheads that you might have from the higher layers?
So that's interesting. I don't think I had like enough awareness of the applications themselves to comment on that. But there is, and as I said, there is like some work on like using let's say smart data transfer, right? Like similar to how you would do for videos, that, okay, I want to prioritize this data from the satellite to the ground station. And in that case, you have to put some compute on the satellite. But I think in our opinion, right, like in our opinion, the better way to do it is to put this like compute on the small ground stations. And then you can think of this as the same application being run from the ground station to the cloud. And the reason for that is the commercial model for a company, right? Like a company like Planet, they don't want to discard their data on the satellite itself. They want to get the data down and then discard it if they need, because the applications are not known a priori right now.
Yeah. But one issue, I think you sort of touched on it, is security, right?
Yeah.
So
that is one issue. I think that is something that we're still like working on, and that would probably be solved in future iterations. Yeah.
Okay. Are there any other questions?
Right now, we don't have any questions on Slack. Maybe I can ask one. So, are there applications where latency is an issue? For example, for space communication, Because,
So,
for example, just maps, it's okay even if I have 1 day old stale map.
Yeah. So I think there are like so many applications where actually latency is an issue. So think about like forest fire estimation, right? That you're trying to detect forest fires and how they're progressing over time. So you need to get this data as soon as possible. One recent one is border conflicts. When there are border conflicts, like if you know, like basically like India and China have this border conflict, and they're relying on the satellite data to like make estimates, and even like public media decides like makes estimates based on satellite data. And all of these are more latency sensitive applications. Disaster management is another one. So in all of these cases, you want to get your data as fast as possible. Few hours is a bit too much for that. Like, and the lower you can get, the better it is.
Great. Maybe we can move on to the next speaker then.
Awesome.
Thanks, Deepak, for the great talk. So next, we are heading for a double header by the same speaker, Debopam. So Debopam is a final year PhD candidate at ETH Zurich and will be on the job market soon. His research focuses primarily on low latency network infrastructures. His work on LEO constellation topology recently received the Applied Networking Research Prize in 2020, and another work on simulating and analyzing these space constellations won the Best Paper Award at ACM IMC. He's here to present his first work on in-orbit computing, an outlandish thought experiment. Over to you, Debopam. Sorry, Debopam, you are muted.
Thanks, Akshay. So let me quickly try to share my screen again. Can you see my slides now?
Yeah, perfect.
Okay, perfect. Thanks. All right. So, hello, everyone. Welcome to my talk, which explores the outlandish idea of adding compute to low-flying satellites, which are currently being deployed to build mega constellations offering internet from space. Starlink, Kuiper, and Telesat are three of many such proposals, which are currently in different stages of development and deployment. While for the first phase, Starlink plans to deploy more than 4,000 satellites in low Earth orbit, or LEO, which is only a few hundred kilometers in height from the Earth's surface, their long-term plan is to deploy more than 40,000 satellites. We ask the question, what if we can add compute to each of the satellites? While there are some interesting use cases, as we'll soon see, even the feasibility of such a deployment is not clearly known at the moment and calls for a more thorough analysis than in our current work. But looking at the brighter side, with this model, no matter where you are, compute follows you. Let us now look at the first interesting use case. This is the current deployment of a large CDN in the US. Compare this to their footprint in the African continent and Middle East. In large parts of the world, CDN edge latencies still exceed 100 milliseconds, which affects end-user experience. Prior work has shown even tens of milliseconds of additional round-trip latency deteriorate web browsing page load times substantially. Fast online multi-tenant gaming QoS depends on latency. Further, for new upcoming applications like augmented reality, latencies beyond small tens of milliseconds are prohibitive. More broadly, many such networked applications that depend on low latency for rich interactivity are being referred to as tactile internet applications. Many of these applications depend on data fetched or processed from nearby edge computing infrastructure with tight latency requirements. Let us see how adding compute to satellites can reduce this edge latency. These are the observer's fields of view in different parts of the world for Starlink Phase 1. X-axis represents the panoramic 360-degree view of an observer, while y-axis represents the altitude or elevation. Different colors of satellites signify different shells, and the blue shaded region marks minimum elevation restrictions. As we see here, even with a minimum elevation of 25 degrees, there are many satellite choices available at each location. One satellite may not offer a large amount of available compute. So this plot quantifies the number of Starlink Phase 1 and Kuiper satellites reachable from a ground location at any time. Starlink Phase 1 will have 4,409 satellites, while Kuiper plans to deploy 3,236 satellites. The solid lines denote average, while the dashed lines denote the minimum and maximum over time. For Kuiper, more than 10 satellite servers would be reachable from any location for most latitudes Kuiper services. For Starlink, more than 30 satellites are reachable from almost all locations at all times. Typically, more than 40 satellites are reachable. In-orbit computing could serve latency-critical application needs by providing low-latency compute access everywhere on Earth. This plot shows the round-trip times from ground locations at different latitudes to Kuiper and Starlink Phase 1. For each constellation, we compute the RTT from a ground location every minute over 2 hours and use the maximum value across these measurements. We do so for the nearest reachable satellite as well as the farthest reachable satellite. The nearest reachable satellite is roughly within 4 milliseconds at most latitudes for both constellations. Of course, these numbers are computed accounting for only propagation delays, so true latencies will be somewhat higher. A variety of applications involve multiple users participating in an interactive activity, such as online gaming, collaborative music playing, learning in a shared online classroom, or more broadly, immersion in the same virtual environment. In these applications, often the multi-user group's experience is contingent on every participant receiving low latency connectivity to the server hosting the application, which we shall refer to as the meetup server. Even using the Starlink LEO constellation to connect 3 users in West Africa to the nearest Azure terrestrial meetup server, we find that the RTT would be as high as 46 milliseconds. On the other hand, the RTT to a meetup server hosted using in-orbit compute on the same constellation would be 16 milliseconds, an almost 3 times reduction. We assume that user terminals can communicate directly via satellites without any gateway intervention like in Starlink. Many applications like Earth imagery, weather observations, and remote sensing generate their data in space. Satellites performing imagery and sensing are capable of multi-gigabit per second data production, but their sensing time is limited by data transmission capacity to ground stations. Pre-processing this data using in-orbit compute could increase sensing time and decrease the bandwidth cost of downloading this data and further processing it terrestrially. This figure shows that more than a third of Starlink satellites are invisible at any time. These satellites are not directly within reach from any of the largest 1,000 cities by population. As intersatellite bandwidth is less constrained than radio downlinks, it allows these satellites to process data cooperatively, thus reducing the downlink bandwidth demands. Okay, having explored some interesting applications in this context, let us see whether satellite compute is even feasible. We compute a commodity server's weight and volume related to that of a Starlink satellite. We use a high-end server S with 64 cores and up to 2 terabytes of memory. Compared to the latest Starlink satellite launched, the weight is 6% of a satellite's weight and the volume is 1%. These are significant costs, but not prohibitive. Of course, this mass and volume overhead means increased mass or fewer satellites per launch. Space hardware needs hardening against ionizing radiation hazards. But ongoing research hints at the possibility of using commodity hardware below the inner Van Allen radiation belt and instead rely on software hardening. For example, the HPE space-bound computer aboard the International Space Station operating at roughly 400 kilometers height is commodity hardware without any specialized hardware frame. Additional power consumption is a big challenge, given satellites already use a combination of solar arrays and batteries to satiate power demands. The high-end server S operating between 225 watts and 350 watts would consume between 15% and 23% of this power. This is quite large, but if necessary, lower wattage servers could be used, or a large solar array and battery could be built in to support this additional power requirement. Another related problem is the increased heat generation. Heat is harder to dissipate without an atmosphere, so additional radiators or thermoelectric harvesters may be necessary. Such additional components will also increase the mass per satellite. Starlink satellites will have a lifespan of 5 years, which is a bit longer than the typical data center server life. If a satellite server malfunctions before its expected life, unlike in a data center, it would not be replaced immediately. However, operators continually replenish their satellite fleet and maintain backup satellites per orbit. Thus, even with a substantial fraction of servers failing, a large LEO constellation could continue to provide valuable in-orbit computing resources. How does in-orbit compute compare to terrestrial compute in terms of cost? Considering the per kilogram launch cost, weight of the server, and the amortization over 3 years, a coarse estimate is that a satellite server would be roughly 3 times as expensive as a data center server. We do not know, however, what the benefit of the scale is. Last but not the least, the dynamic behavior of LEO constellation poses a challenge. If a satellite is now over eastern Brazil, in 6 minutes, it will already reach Africa, crossing the entire Atlantic, traveling more than 500 kilometers per minute. Due to this dynamic behavior, a particular meetup server is only reachable by clients for a few minutes, after which a handoff is needed to a different satellite. This handoff is different from cellular or Wi-Fi handoff due to the additional mobility of the network infrastructure. Note that trajectories are highly dynamic yet predictable. By virtue of regular handoffs, a series of LEO meetup servers can expose to clients an abstraction similar to geosatellites, stationary operation at roughly the same location over time. The naive min-max approach for selecting a meetup server picks the latency optimal satellite at each instant. It minimizes the maximum latency across a set of clients connected. However, min-max suffers from potentially frequent handoffs to successor meetup servers. An alternative heuristic, Sticky, prioritizes stationarity by planning ahead, leveraging predictable satellite motions. It computes the set of meetup servers that provide latency within 10% of min-max, orders them by the longest time until handoff, and among the top 5, picks one which would result in the least latency for handoff to its successor. For the 3 users in West Africa use case, Sticky substantially decreases the frequency of handoffs at the cost of less than 10% latency inflation, while the latency for state transfer to the successor remains similar across Sticky and min-max. To conclude, the mega constellations can host sizable aggregate compute, thus enabling low latency compute access from everywhere at any time. This can be attractive for some applications, given many potential issues are not too prohibitive. Yes, we know this is an outlandish idea, but what is your take on this? We know that there may be unknown unknowns that could potentially make in-orbit compute entirely infeasible. So we are open to both killer objections and interesting application ideas leveraging such an infrastructure. Thank you for listening. I'm now open to take questions.
Yes, that was a fascinating talk. Thank you. Any questions? I'm sure there are lots of questions. So
there is a question on Slack by Kevin Glavin. Is power budget the largest problem for significant CPU processing? 15 to 23% of the power is huge, and adding more solar must affect the economics of the satellites. Will the user in Africa really pay for this additional overhead?
So that's a very good question. Regarding the power budget, like 15 to 23%. So these are kind of numbers which are somewhat back of the envelope. It's what we used as numbers is like from the openly available data from NASA, and what the solar cells in the International Space Station look like, and what power efficiency they have. But the efficiency at which we assume Starlink to be operating is roughly 6%. And there are commercial kind of solar cells which are already available and being advertised by different companies, which are offering efficiency of roughly 30% or so. So there is a possibility of increasing the efficiency of solar cells even when it comes to these new mega constellations that are being currently deployed. Now, of course, this would also increase the cost. The question is whether the end users, the users of the applications, would be ready to pay this amount. So that's a good question. And I think it really depends on the market whether these companies would shoot for compute in satellites. But it's like what we claim here, or what we say in the paper is like, there is nothing prohibitive from deploying compute in satellites. The question is, do we really need that compute, or whether it's feasible to put that compute in space? Yeah.
Yeah, so I have a segue question, because our first speaker just 2 talks ago said that, hey, like edge computing latency is a bubble, it's not that big a problem. So do you have any comments on like what kind of applications do you envision where these kind of latencies would be actually prohibitive?
Yeah, so we mentioned a couple of applications. For example, fast online gaming, where tens of milliseconds can impact the QoE that users have, right? So So there are some games which would need, for example, each user to have some latency for communicating, and beyond that threshold, things would not be feasible. So when users join a room online, they would be going through a phase of matchmaking where users with similar latencies would get connected. So that's one thing. And another thing is, like, when it comes to certain games, for example, these would try to reduce the variation across users in terms of latency, right? So gaming is a big example. Other than that, collaborative immersion, AR, VR. So these applications would be very interesting. But coming back to the edge latency, what I would say is, like, the numbers have improved over the last 10 years. That's true. And we are not like beyond 200 milliseconds or so. So the edge latency is improving over time. But, I mean, with these new space constellations, a large fraction of the global population would get connected to the internet. So the same provisioning problem that CDNs or edge face these days, that provisioning problem would need to be solved again for the newly connected population. So this would take some time. So the edge latency would need to improve for the newly connected global population.
What does the bandwidth look like?
So the bandwidth, as advertised by Starlink, for example, is 20 Gbps per Starlink satellite downlink. But I mean, given there are more satellites than one at any location, so we have seen that there are 40 plus satellites at most of the locations for Starlink, and that's the first phase of Starlink. So that the aggregate bandwidth would be still quite high.
But I mean, what Deepak was just saying, right, the last talk, that, whenever they meet somebody, they just want to push a lot of data because they collect a lot of data. So so in your case also, they're presumably also sensing and collecting data that they need to send. So they need to do both of these. So you'll also have to think about how to schedule that if this works out, right?
Yeah, so that is true. I mean, so we in this paper advocate for space native data processing. But I think, I mean, it's not only about data processing, it's also about compressing data in space and then trying to improve or reduce the bandwidth demands that these applications might be having.
Sure. Okay, I think that's it. There's a lot of discussion on Slack, so you should go and, of course, after your next talk, I guess, go and answer this question. So thank you.
Yeah, so as I said, this is a double-header presentation session. And now, after speaking about how we can add compute resources to the satellites, now he is presenting his work on providing internet from space without inter-satellite links. So back to you, Deepak.
Thanks. Can you see my slides? Perfect. Okay. So welcome to my second talk on the impact of inter-satellite connectivity in large mega constellations. These constellations, as we all know by now, consist of thousands of low Earth orbit or LEO satellites and aim to beam internet from space. SpaceX Starlink is being currently deployed at a pace of 120 satellites per month and is months away from providing service. They have already started beta testing. Most of these constellations bank on laser inter-satellite connectivity for long-distance data transfer possibilities. Products offering laser inter-satellite links, or ISLs, at 10 to 20 G at distances up to 8,000 kilometers are already being advertised. Multi-gigabit laser ISLs have been demonstrated successfully on multiple locations in the past. These are usually silicon carbide components mounted on the satellites and are discussed in the initial FCC filings of SpaceX. End-to-end paths in constellations supporting ISLs would consist of a radio uplink from the source S to the ingress satellite, followed by 0 or more laser ISLs, and then the egress radio downlink to the target T. Two positional papers at HotNets 2018 discussed the utility of having ISLs in these new space LEO constellations. They showed that by virtue of speed of light laser, end-to-end latencies would be reduced significantly compared to today's internet. Let us see this in action. In this example, we are seeing a path between Zurich and Mumbai over satellites, which is quite close to the geodesic compared to fiber, which is roughly 2x longer. The speed of light being 2/3 in fiber compared to free space means that the fiber path will be 3x higher latency. Despite this high bandwidth, low latency ISL promise, there is substantial uncertainty about whether or not they will successfully incorporate ISLs. One hurdle may be the burn on re-entry requirement that regulators are asking operators to satisfy, thus not risking injury and damage from deorbiting satellites. In response, Starlink's filings were amended to exclude mention of these components. None of the hundreds of already deployed Starlink satellites feature ISLs. Luckily, LEO networks do not need ISLs to provide service. One might think how to achieve long-distance end-to-end connectivity when there are no ISLs. Remember, as the constellations are being rolled out, ground terminals would also be rolled out. These terminals include user terminals on land and those mounted on airplanes and ships, and also more powerful ground stations. Without ISLs, connections between far separated ground terminals bounce up and down between satellites and on-path terminals, yielding a bent pipe or BP connectivity. What is amazing is that latency lower than terrestrial internet can be often achieved over long distances, even with this restricted BP connectivity. Mark's paper in HotNets last year focuses primarily on such latency benefits. However, in this work, we quantitatively show that even with dense ground station deployments, there are 3 very significant downsides to foregoing ISLs. Although LEO networks without ISLs still provide low latency between many ground locations, the temporal variation in latencies increase substantially. The network-wide throughput decreases heavily, and the network becomes more vulnerable to weather disruption because of transit through satellite ground links. We also analyze the hybrid approach, which uses both ISL and BP connectivity in end-to-end paths. For running our simulations, we use Starlink's first shell, which consists of 72 orbits and 22 satellites per orbit, and operates at a height of 550 kilometers and inclination of 53 degrees. And Kuiper's first shell, which consists of 34 orbits and 34 satellites per orbit, and operates at a height of 630 kilometers and inclination of 51.9 degrees. At each of the 1,000 most populous cities, we place ground terminals, which are traffic sources and sinks. We pick 5,000 random city pairs for our experiments. Also, GTs, which only transit traffic, are placed uniformly every 0.5 degree on the latitude-longitude grid within a radius of 2,000 kilometers of the cities. In addition to these GTs, to help BP achieve transoceanic connectivity, we use all in-air commercial aircrafts as GTs. For this, we use flight hours data for a period of 1 day from 2018. For the latency and the latency variation results, we simulate the network for 1 day. At every 15-minute snapshot, we find shortest paths between the 5,000 city pairs. As seen in this plot, the minimum RTT is strictly lower for the hybrid approach as expected, although they are mostly comparable. There are, however, substantial differences in the tail, the maximum difference being 57 milliseconds. With exclusively BP connectivity, some paths see high latencies due to suboptimal intermediate hops. Next, across time snapshots, we compute the max minus mean RTT difference for each city pair and show the distribution across city pairs. The results show that latencies vary much more with exclusively BP connectivity. While with hybrid connectivity, the maximum range of RTTs across city pairs over time is under 20 milliseconds. With BP, this range is as high as 100 milliseconds. With BP, the path between Maceió in Brazil and Durban in South Africa sees an inflation of 100 milliseconds over time. This is because the density of air traffic is much sparser over the South Atlantic than the North. Hence, the path often ends up using aircrafts flying over the North Atlantic as intermediate hops. Note that this behavior not only inflates the RTT of this path significantly, but also makes the heavily used paths over the North Atlantic even more congested. Let us now compare the aggregate throughput offered by LEO networks with BP-only connectivity and hybrid connectivity. For each of the 5,000 city pairs in our traffic matrix, we route traffic over the k h-disjoint shortest paths. Traffic between each city pair uses k subflows, each along one of these k paths. These subflows are treated independently by the simple max-min fair share algorithm, which iteratively and greedily finds the most congested link in the network and shares the bottleneck link capacity fairly among the competing flows. ISLs are 100G and up-down radio links are 20G. For only shortest path routing, the hybrid approach achieves more than 2.5x higher throughput than BP for both Starlink and Kuiper, while with K equals 4, this improvement is even larger, at least 3.1x. Besides the use of scarce GT satellite capacity for transit, in addition to only sourcing and syncing traffic, another reason BP fares poorly on throughput is that, at any time, it is unable to utilize a large fraction of the satellites for networking at all. For Starlink, we find that across a day, the number of satellites that are entirely disconnected from the rest of the network varies between 25% and 31.5% of all satellites. For analyzing the impact of weather on satellite connectivity, for each of the 5,000 city pairs, we find the shortest paths using Dijkstra's algorithm. Next, we find the worst attenuation seen across all links in the path. For paths consisting of ISLs, this value is either the first or last hop attenuation, whichever is worse. But for BP path, this is the worst attenuation seen across all links of the zigzag path bouncing between the satellites and GTs. We use the ITU RPi library to measure the attenuation for GT satellite paths. This library implements ITU recommendations to model atmospheric attenuation due to rain, cloud, gaseous cover, and tropospheric scintillation in slant paths. For the ISL paths, we exclude GTs as intermediate hops in order to quantify the maximum improvements in attenuation possible with ISLs. We assume that the signal for BP paths uses error correction and regeneration at each GT. Otherwise, the multiplicative impact of attenuation would be prohibitively high. The Delhi-Sydney path covers the tropical region, which experiences high annual precipitation. The heat map depicts 99.5th percentile attenuation across Southeast Asia. Although both endpoints, Delhi and Sydney, are in low attenuation areas, BP ends up using intermediate hops in regions with higher attenuation. In contrast, the ISL path avoids this entire high attenuation region. This plot shows the attenuation along the path. Y-axis plots the attenuation, and x-axis plots the percentage of time the attenuation value is exceeded. At least 1% of the time, the BP attenuation is 5 dB, while ISL attenuation is 2.2 dB. Note that 1% translates to 88 hours per year. There are various other benefits of ISLs which BP struggles with, which I briefly touch upon. BP connectivity between certain sources and destinations is bound to require GTs in countries and regions that an operator would like to avoid, either because of challenging topography or due to political reasons. Ka and Ku band radio spectrum for the up and down links needs licensing. In contrast, thanks to the narrow beams and negligible interference issues, intersatellite laser connectivity is unlicensed.
2 more minutes.
Sure. GSO satellites fly above the equator and operate in the same frequency bands sought for LEO communication. Thus, LEO satellites, when crossing the lower latitudes near the equator, must avoid interference with GSO satellites. While GT field of view is already restricted by the minimum angle of elevation, GSO arc avoidance makes this field of view even more restricted. The impact of this will be much higher on BP than on ISL connectivity for traffic between the northern and southern hemisphere. Here is the latest update on the status of ISLs. In their September 3 launch video, a SpaceX personnel announced the testing of laser ISLs in LEO. But a lot of uncertainties regarding ISLs still exist. What would be the link capacities in practice? Link setup is constrained by the fact that it takes a few seconds to tens of seconds to establish these laser ISLs. How do we connect satellites using ISLs, keeping in mind these constraints? Our CONEX 2019 paper attacks this problem. Our work is also relevant for constellations like OneWeb, which do not plan to incorporate laser ISLs. It will be interesting to see how these constellations evolve over time and stand by their promise of global internet connectivity. With that, I thank you for listening.
All right. Questions? Okay, so my questions, and I read your CONEXT 2019 paper, it was very interesting. My question is that, so what are the disadvantages of using intersatellite communication? Is it the fact that the communication itself is now hard and you need to start to schedule it, or is there a cost issue, or why did you do the study? In the sense that, like, people must have said, I don't want to use ISLs, which is why you did this study. So why are
Yeah, sure. So to recap, basically, intersatellite links would need some components, some communication components, which are silicon carbide. So there are some recent requirements from FCC and ITU and these governing bodies that satellite constellations should make sure that there is complete burn-up on re-entry. So when the satellite is getting deorbited at the end of its life, nothing should come back to the Earth surface. So that's the reason SpaceX also amended their recent FCC filings, and they removed any discussion on the silicon carbide components. But what is interesting is, like, they recently announced in one of their launch videos that they have already tested inter-satellite connectivity. So we do not really know what are the components that they're using for this kind of connectivity.
I see. So your take on this is that that they have to figure out a way to do this because it provides you a lot of benefits.
So that is true. I mean, even without inter-satellite connectivity, these constellations would survive, but that would not untap the full potential of these constellations.
So I just want to understand, like, there must be some catch in, like, just using the BPs to kind of do communication. What's the catch? Do you get lower throughput, higher latency, or what is?
So with BP, I mean, the catch here is, like, if you are using BP exclusively, then the problem is the up-down radio links are a lot more bandwidth constrained, right? So if we are using inter-satellite links, because this is laser in higher layers of the atmosphere, the bandwidth that they can offer is quite high, right? So BP suffers from this bandwidth constraint, and because it's like a global traffic matrix, and you were using this zigzag connectivity, that would, like, already be a lot of overhead for these up-down links, which are, if there is a constellation which has ISLs, then the up-down links are only the last and the first hops, but now they're also being used for transit, right? So this is a problem that I see.
Okay, Matt, I'm asking you to unmute. Okay, yeah.
Hi, this is a super interesting talk. I love all these talks
Matt.
about satellites and satellite routing.
Mm-hmm.
I was curious, in your analysis, did you consider inter-satellite links that essentially skip like an intermediate satellite, or is there any advantage to doing so?
Sorry, I didn't get the question. Can you elaborate a bit?
Essentially, like, in the pictures you drew, at least, it looks like the inter-satellite links always went sort of between the nearest two satellites. And so you had a hop that was 5 satellites long. In the constellations, is that the least number of hops that are possible, or is it possible that you could have an inter-satellite link that skips one of the middle satellites?
Yes, that's a very good question. So at least in the context of this work, we didn't try that. But we have an entire paper in CONEXT 2019 where we discuss, like, this possibility of using longer hops. So it's basically a motif-based work. So the solution is kind of to use motifs, different motifs, or different types of connectivities where you use longer hops instead of the immediate hop that's in the plus speed baseline connectivity, right? So yeah, that does improve the performance in terms of the throughput that it could offer, and also latency sometimes.
Giacomo, you can unmute.
Yes, hello. Do you hear me?
Yes.
Hello. Hi, thanks for the great talk, the great 2 talks. So I was wondering, in this BP or hybrid connectivity, do you have any intuition or any speculation on how the routing would actually look like? Because, these satellites have multi-beam antennas. And so if you would need to sort of bounce the signal off a user terminal, you would need to somehow agree or find a way that both satellites can triangulate or know that there's a user in view of the next satellite or something along this direction.
Yeah, sure.
And the computation should be online and very fast, and also it could not be sort of done ahead of time, at least for the mobile terminals, right? So I wonder if you have an idea about how this routing could be done.
Sure. So that's a very good question. I mean, ideally, these would require terminals that can talk to at least 2 satellites, right? So, yeah. So basically, what happens is like these terminals, these user terminals, would be using 2 different beams to communicate to 2 different satellites, and this might be the same frequency or a different frequency depending on the angle of separation. But when it comes to routing, I mean, we only have tested shortest path and k shortest path, but there is scope beyond that. We can try different things. But what I think is like when you ask this question, it was more about frequency allocation and how user terminals would be kind of participating in this entire routing online, right? So this is something we have thought of, but we have not dealt with in the paper in this work. So this is left to future work. But yes, I agree to your point that the user terminals should be able to use different frequencies to communicate to different satellites in order to be an intermediate hop.
Of course, but my question was more in the direction of, since these user terminals are mobile, can change position, can change density in an area, for example, even online, and this is not predictable, to use the shortest path algorithm, you need to construct a graph. And this graph is not, it has to be constructed in real time. And this seems like a very expensive task. So do you have any intuition on how this task can be carried through?
Yes, so that is true. What we kind of did is like, we did this at some discrete snapshots of time. And then, I mean, it's kind of trivial. But online, because if we are using airplanes as intermediate hops, which are moving, the position would change with time. But the point is, like, when it comes to the mobility of airplanes and even ground terminals which are moving, that takes time, right? I mean, compare that to satellites moving. So even if you assume for a span of time, which is like few seconds, even if you assume the aircraft to be fixed, it would definitely be not optimal, but it would still give you good results.
Okay, I think we're running out of time, but thank you for these great discussions, and please continue discussing on Slack as well as after during the breakout session. So Akshay?
Yeah, so those were great 2 talks. They were amazing. So our next and final speaker of HotNets 2020 is Carol. Carol Su is a 4th-year PhD student from Georgia Tech, advised by Ada Gavrilovska. The research areas she focuses on are edge computing and container orchestration. She's not on the job market, but is looking for internship opportunities. So if anybody is looking for interns, do reach out to her. A fun fact about her is that it's her birthday today. So to save you from my voice, I would like to play a 20-minute happy birthday jingle for her birthday. So, Carol, happy birthday, and over to you to tell us more about why DNS does not suffice for MEC CDNs.
Yeah, thank you. So can you hear me clearly?
Yes.
Okay, so thanks for the song. So can I have like 20 seconds more than my presentation?
Don't worry, I'm keeping the timer, don't worry, you have a lot of time.
Yeah, thank you everyone for coming to join this final session of HotNet. And yeah, let's come back from space to Earth. So today I'm going to present our work. DNS does not suffice for max CDN. So first I'm going to tell you that why DNS processing CDN in edge compute cannot satisfy edge computing requirement. And I will present our new design for CDN at edge. Mobile edge computing, in abbreviation, we call it MAC, has proximity benefit to shorten end-to-end latency. One example is like here, AR/VR gaming. Application provider can put partial data and computation at edge location. So client's request could be resolved at edge, then provide a shorter response time. The round trip time here is target to meet 20 milliseconds requirements. Max deployment is a good match for emerging latency sensitive workloads. CDN is one of them, and it's also a common and reliable system already. So if we want to serve CDN cache at edge location, ideally CDN system can provide a shorter response time when data query, when the cache hit. And it is also can provide a data locality feature for applications. So before we talk about how we support CDN system at edge, let's first take a look at the CDN process. Cache instances are located in closer to users. So when mobile user, they've tried to fetch CDN content, first, the request will go to LDNS. LDNS is provided by mobile cellular provider, and it is the default DNS server to mobile users. So mobile users' cache discovery could be resolved quickly at LDNS if it has already has cached the domain name and the IP mapping. If not, this request will go to CDNS, the CDN router. CDN router is one of the components in CDN system. When you got the request from clients, it will quickly resolve the nearest cache instances specific for these requests. But we still need authoritative DNS server, the ADNS. It is because the cache could be stale. So we need ADNS help to find the original content server to update the cache. To summarize, we can know that based on this basic CDN process, to achieve high performance CDN, we not only need to getting content cache hit, we also need to do a fast DNS resolution among these three servers. Now let's focus only on the cache is fresh. So to serve CDN cache at edge location, the straightforward way is that we move cache instances at MAC platform. So when the cache hit, we can have a fast end-to-end data query latency. However, what about DNS resolution? Do we need to support a new system design for serving fast DNS lookup time? So now I want to share a set of experiments we did for the DNS process in mobile network. So to look at, to evaluate the CDN's DNS process in mobile network, so we try to fetch the CDN-enabled web content and count how fast we can get the DNS domain name resolution. So along with wireless mobile communication, we have two other connectivities here, the wired network and the wireless communication through Wi-Fi at home. So as a result shown here, we can see that wireless communication through mobile network cannot meet the 20 millisecond edge computing requirement. And it is also the most unstable one. However, we can see the other two network connectivities. They roughly meet the 20 milliseconds expectation. And so this gives us the idea that there is possibility that we can improve the mobile user's CDN experience. We take a further look at what's the result we got from these numbers. So I show two new figures here. The three network connectivities now shown at the y-axis. different colors means different subnets we got. And different tones of the colors means the subnets is from different CDN providers. So like here, Airbnb, we can see that even if we fetch a single static content, it relies on two different CDN providers. One is from Akamai, shown in yellow, and one is Fastly, shown in blue. So this shows us that even if we are at the same geolocation, fetching the same static content, using different network connectivities leads to different low balancing frequency among the different data center of a single provider or from different provider. And this complexity turns out to have a high cache miss rate when we update the content or when CDN providers serve separated requests. So to summarize, our Mac CDN need a new system design that supports both low DNS process latency and also high cache hit rate. So now I want to introduce our Mac CDN design. First, to have a fast cache request resolution, we decide to move LDNS at Mac location. It is because LDNS at Mac location can fast differentiate that this client request is to internal Mac service or external endpoints. And also, we decide, since our cache is on Mac location, we also propose that CDNS is also need to be put at the Mac location as well. Then it can shorten the end-to-end latency, like from LDNS to CDNS and CDNS to clients. And so if using our Mac CDN design, most of the CDN requests at edge could be solved within Mac platform and support shorter response time. We use Kubernetes as our testbed. So every function you see here, like radio network functions and CDN components, all of them need to be containerized and served as Kubernetes services. And we decide to use core DNS, the Kubernetes default DNS server, as our LDNS. It is because it natively takes charge of service discovery for internal functions. Now I want to show the latency comparison of CDN DNS lookup between our Mac CDN design to other LDNS and CDN DNS deployments. Here I show the first three latency is that we use general DNS server without CDN involved. We can see that LDNS at LAN, the local area network, it has the most stable latency. However, Google DNS, since it's wide adoption, so it has a comparable latency to LAN LDNS. Now I see a new top bar. It is that we move LDNS at Mac location and with cloud CDN. And I forgot to mention that the latency we discriminate into two parts. The yellow part is wireless communication, and the blue part is DNS query time. So if we only focus on the DNS query time for this new bar, we can find that it has more than 2 times speed up than other bars. And this deployment is also proposed in latest HC white paper. So now I show 2 new deployments is that we put LDNS the same at the Mac platform, but we move CDNS to a closer place. The first part is that the CDNS is also in Mac platform, so the first part is our deployment. And the second one is the CDNS is at LAN. So these 2 bars has drastically improved than the other ones. And if we only focus on the DNS query time, we found that our deployments has even better, like reduce about half of the time than CDNS. And if this deployment is in 5G network, we can much more shorten the wireless communication, the yellow part here. So it makes our improvement more significantly. We also have an additional benefit. Since every function is within the same container orchestration, we don't need to publish any of the function when solved client's requests. To summarize our work, first we evaluate DNS lookup latency of current CDN process in mobile network, and we found that the latency cannot meet the edge computing's requirement, the 20 milliseconds one. And CDN's ecosystem is complicated, and this complex and multi-ownerships makes it is an obstacle for optimization. So to solve the problem, we present our next CDN design, and we show that it greatly reduces the DNS query time compared to current cloud solution or ETSI white paper. And we also improve that it is important to put LDNS and CDNS at MAC location. For our future work, we want to evaluate our design with more detailed CDN process, like how we update the cache at the edge location. And also we want to move our design to a more realistic testbed and to coordinate with multiple Mac workloads. Yeah, thanks you for your time, and we are going to take any feedback from you.
Thank you very much. This was a fascinating talk. I really enjoyed the measurement study you made. While we wait for questions, I don't know, maybe I missed this, but why is the DNS lookup so much worse on cellular compared to Wi-Fi and the home network?
Yeah, it is because that we think that the first is that there is the latency difference between wireless and wired connection. And also there's multiple ownership since there will be several DNS servers involved. So actually we don't know where is the cache instances. Maybe it returned to a not that close one. And also the DNS resolution is, we cannot guarantee that it is the fast time among the servers.
I see. Yeah, this is very interesting because this might be why the web is like one reason for web page loads to be slower on LTE might be also because of the DNS time. But okay, so there's a question from Aaron. I've asked him to unmute. Yes, go ahead.
Hey, I'm Aaron from Colgate. Interesting observations here. So I'm curious if there are other apps. So I realize that CDNs are used to using DNS to address sort of the load balancing and assignment, but are there other things that we should be doing in a mobile environment where there's sort of more control over traffic rather than this sort of design with DNS? Should there be other ways that we should be routing traffic to the desired CDN nodes?
Yeah, so this is also the reason why we want to put cache instances at the MAC location. It is because we want to guarantee that the closer one is the correct one. So if this user is moving with their mobile, so it come across to the nearest base station and it got the right cache. But if when they move to another base station, actually there should be another nearest cache around the closest base station. So actually here we also simplify the routing because the right data is in the right place. So we don't need to transfer these packets around. It can, do I answer your questions correctly?
I think. Oh, Aaron is muted again. I can ask him to unmute again.
I think sort of. I think what I was getting at is, can we cut DNS out of the mix, and can we just do routing tricks in a mobile network? Is I think really the question that I'm asking.
So your question is that to increase the routing time in the mobile network?
To eliminate the latency that comes from DNS entirely by effectively somehow allowing the devices to do routing and to skip the DNS lookups, to just do something like Anycast routing almost for contacting the CDN.
Yeah, I think current DNS lookup already has Anycast mechanism inside, but as we can see that actually this cannot don't improve that much based on our numbers.
Okay.
I had one last question. Just make sure nobody else has a question. Yeah, okay. Is that how easy or difficult is it to you to put this CDN caches in the edge, right? Like, I'm assuming it's not that easy. You might have to do some kind of, you talk to these CDNs. Like, yeah, I have wanted to get a sense of how easy you think this is.
Yeah, in our test bed, we use Apache Traffic Control as our CDN system.
Okay.
So, yeah, we believe that when a cache is updated or there's a new cache join in the whole system, there is some delay, like across the internal components. They may need to handshake and need to update the backend database. But this is also one part that we try to eliminate the time to support a faster deployment in our environment.
Okay, thank you. Thank you, Carol. That's our last speaker. Thank you for the session, for the rest of you for staying around. I think I'm going to hand it over to Harsha.
Yeah, thanks, Aruna. So I guess before we kind of head into our final breakout rooms, just wanted to thank all of you for taking the time the last 3 days to attend HotNets. Hopefully it's been a useful experience. And also on behalf of my co-chair, Venkat, who's understandably probably off to bed at this point. It's close to 11 p.m. on Friday night back in India. On behalf of him and I would like to thank a bunch of people who have been involved in making this event possible. Most importantly, perhaps, is Tom and Caroline, who's been instrumental in keeping all of this infrastructure up and running. So maybe everyone can try unmuting yourself and just giving a round of applause, or even virtually. And of course, I would also like to thank Heather and Ben, who have put in a lot of hours into setting up this multi-mode of interaction via Zoom, the live streaming on YouTube, and setting up the Slack workspace. So Heather and Ben, really thanks to you for all the work you've put in over the last several weeks. So just wanted to also point out that the Slack workspace will remain. We plan to keep it around for at least the next couple of weeks. So feel free to use that as a mechanism to interact with the authors, ask them questions. Maybe in a couple of weeks, then we will archive all the content, all the publicly on the paper specific channels, and probably post it on the website along with all the videos of the talks. Heather or Ben, did you want to add anything more before we wrap up?
I just want to thank everybody for attending the conference, and especially kudos to Venkat and Harsha for setting up this fantastic program, to all the PC reviewers, and thanks everybody. And it's a lovely day here at Chicago, and hopefully tomorrow will be even brighter. So thank you very much, and then I would like to wish everybody a great weekend, and happy Thursday to Carol. And I guess with no further delay, we'll send everybody to the breakout room. Thanks.